Some nights the sky holds a kind of stillness that feels almost deliberate, as though the darkness itself has slowed down, and the stars above have been waiting quietly, patiently for someone to simply look up. If this feels like a good place to rest tonight, you are welcome to stay. Now, let's drift. There is something the universe has been holding back, not out of secrecy, not out of mystery for its own sake, but simply because we, for most of human history, did not yet have the instruments to receive what it was already sending. And what we've begun to find in the last few decades in the careful light collected by telescopes drifting far above the Earth is a picture of the cosmos so different from what anyone imagined that some of the most experienced astronomers have admitted quietly, and with something that sounds almost like wonder, that they are not entirely sure they understand what they are looking at. That is where we begin tonight, not with certainty, not with conclusions, but with the gentle, unhurried act of looking. For a very long time, our understanding of the universe was built on what we could observe with instruments that were in cosmic terms barely more than eyes. Early telescopes revealed that the faint, smudged patches of light scattered across the sky were not clouds of gas within our own galaxy. They were in fact entire galaxies themselves, separate islands of stars, each containing hundreds of billions of suns, separated from us by distances so vast that the numbers lose their meaning if you try to hold them too firmly. The Milky Way. Our galaxy, the one we live inside, is home to somewhere between 200 billion and 400 billion stars. Researchers have found it difficult to count them precisely because we are embedded within it, and counting stars from the inside of a galaxy is something like trying to count all the trees in a forest while standing among them in the dark. But the rough outline is clear enough. Enormous, ancient and spiralling slowly through space, on a journey that has already lasted longer than the Earth has existed, and for a while it seemed reasonable to assume that other galaxies were more or less variations on this same general theme. Different sizes, different shapes, some spiraling like the Milky Way, some elliptical and soft at the edges, some irregular and loosely formed. But all of them following the same basic rules. All of them made of stars' gas and the kind of matter that responds to light. It seems that assumption, comfortable as it was only ever a beginning, because when astronomers turned newer, more sensitive instruments toward the deeper sky telescopes that could gather light over hours and days, telescopes carried into orbit to escape the blur of the atmosphere, what they began to find did not always fit the pattern. Some of what they found did not fit any pattern at all. There are galaxies out there that should not by any current model of how the universe forms and grows exist in the way that they do. Galaxies that are the wrong size for their age. Galaxies that contain almost no visible matter whatsoever, and yet hold together as though something invisible is threading through them, keeping them intact. Galaxies that look as though they were made by a process no one has yet been able to explain. Galaxies that glow with light from an earlier era of the universe when the cosmos was still very young, and yet which carry the internal structure of something that has been quietly aging for a very long time. Scientists are still exploring what these objects mean, whether they represent rare exceptions, strange corners of the universe that formed under unusual conditions, or whether they are in some way pointing towards something more fundamental that current physics does not yet fully describe. The answer as of now is genuinely unknown, and there is something quietly reassuring about that. About the fact that the universe is still after everything we have learned larger and stranger than the models built to contain it. The mind, when it first encounters an idea like this, often reaches for comparison. We are built for pattern recognition, for the comfort of the familiar. And so when we hear that there are galaxies which should not exist, something in us wants to resolve the strangeness quickly, to file it away in a category to make it make sense. But the scientists who study these objects tend to do the opposite. They sit with the uncertainty. They return to the data. They revise their models carefully, slowly, without rushing toward conclusions. It may be that the most productive thing the human mind can do when faced with a genuine mystery is simply to remain curious without demanding an answer. That is in its own way a kind of rest. What we'll move through tonight is not a lecture and it is not a list. It is something closer to a slow walk through the stranger edges of what is known and into the softer territory of what is still being discovered. Each object we encounter has been observed by real instruments, documented in real studies, and puzzled over by researchers who have spent years, sometimes entire careers, trying to understand what they're looking at. And yet, for all that careful attention, these galaxies retain something that feels, even in the dry language of scientific papers, almost like a quality of strangeness, as though the universe in making them allowed itself a kind of freedom, a deviation, a shape that was not in the original plan if there was ever a plan at all. The sky above is full of these deviations. Most of them are invisible to the naked eye, too faint, too far too strange in their composition to announce themselves in the ordinary light of a clear night. They require patience and instruments and the slow accumulation of signal over time, but they are there. They have always been there, travelling toward us on light that left its source millions, sometimes billions of years ago, carrying information about a time when the universe was arranged differently than it is now and about processes that are still in some sense unfolding. There is particular quality to that kind of distance. When astronomers observe a galaxy that is, say, 500 million light-years away, they are not seeing it as it is. They are seeing it as it was 500 million years ago, when the light they are now receiving first left its source. The galaxy they are looking at may have changed entirely since then. It may have merged with another galaxy, or scattered its stars across the void, or collapsed inward under its own gravity. What the telescope shows is a kind of memory, a preserved image of something that existed long before the first animal on Earth looked up and wondered what the points of light in the darkness might mean. We are in a very real sense looking at the past every time we look at the night sky. Even the light from our nearest stellar neighbour takes a little over 4 years to reach us. The light from the Andromeda Galaxy, the largest galaxy visible to the naked eye on a clear night, left its source approximately 2.5 million years ago. Long before the first stone tools, long before the first human voice. Researchers have found that this quality of cosmic observation, the fact that greater distance always means looking further back in time, is one of the most powerful tools available for understanding how the universe evolved. By comparing galaxies at different distances, astronomers can in effect watch the history of cosmic structure unfold across billions of years of time. And within that history, the strange galaxies are among the most informative precisely because they are the most unexpected. They are the places where the story seems to skip a beat, where the pattern gives way, and in those gaps there is often something worth understanding. The night is long and there is no urgency here. What we're doing is simply looking carefully, gently, with an openness to whatever the light has carried across all that distance to show us. Somewhere in the darkness above, beyond the familiar arc of the Milky Way, there is a galaxy that is almost entirely invisible, made not of stars, not of glowing gas, but of something we cannot see directly, something we can only infer from the way it bends and holds. And the fact that it is there, the fact that it is real and patient and holding itself together with matter that has never once emitted a single photon of light, says something about the nature of the universe that feels, even after careful consideration, a little like encountering something new in a room you thought you already knew. That galaxy is where we are headed next, and what scientists found when they first observed it, and what they're still trying to understand about what it means, is something that begins not with a dramatic discovery, but with a quiet question about why a certain patch of sky looked slightly wrong. You said ban la chuyen gya viet kich bantingan ke chue hoa hok trus kingu tren ken YouTube, ban como sak ke chuyen joke jau haptan rieng beat mangjamd. Before we go further into the strange, it helps to spend a little time with the familiar. Not because the familiar is less interesting, but because the mind settles more easily into wonder when it has somewhere steady to stand first. And there is, it turns out, something genuinely remarkable about even the most ordinary galaxy, if such a word as ordinary can be used for something containing hundreds of billions of suns. A galaxy is at its most basic a gravitational family. Stars drawn together over immense stretches of time, orbiting a common centre, moving in patterns so large and so slow that a single orbit can take hundreds of millions of years to complete. Our own Sun, for example, has been travelling around the centre of the Milky Way for the entirety of its existence, and in that time it has completed somewhere between 20 and 25 full rotations. 25 laps around a track so enormous that the numbers, if you try to hold them in ordinary terms, simply dissolve. Researchers have found that galaxies are not random collections of stars scattered haphazardly through space. They have structure, they have architecture. They tend to form in ways that follow patterns. Patterns shaped by gravity, by the distribution of matter in the early universe, by collisions and mergers, and the slow accumulation of gas over billions of years. There is in the formation of a galaxy something almost like a logic, a set of conditions that leads reliably to a recognizable outcome. The most familiar shape, the one that comes to mind when most people picture a galaxy, is the spiral. Two or more curved arms of stars winding outward from a central bulge like the surface of a slowly turning pinwheel seen from above. The Milky Way is a spiral. So is the Andromeda Galaxy, our nearest large neighbour, moving toward us through space at roughly 110 kilometers per second, a speed that sounds alarming until you realise that the distance between us is so vast that the two galaxies will not fully merge for another 4 billion years or so. There is time. There is always in cosmology more time than the imagination can comfortably accommodate. Spiral galaxies form their distinctive shape through a process that scientists are still exploring in detail, but the broad mechanism is understood. As a galaxy rotates, the stars within it do not all move at the same speed. Those closer to the centre orbit faster, those further out more slowly. And this difference in orbital speed, what astronomers call differential rotation, produces the sweeping curves of the spiral arms. The arms themselves are not fixed structures like the spokes of a wheel. They are more like waves, regions of slightly higher density where gas compresses and new stars form moving through the galaxy. The way a wave moves through water, the water itself does not travel with the wave, but the pattern does. It may be that this is one of the more quietly profound things about spiral structure. It is not a thing exactly. It is a behaviour, a pattern that maintains itself not because the same material is always in the same place, but because the conditions for the pattern keep being recreated as the galaxy rotates. Beyond spirals, there are elliptical galaxies, rounder, smoother, more uniform in their distribution of stars. They tend to be older, quieter, no longer forming new stars at the rate they once did. The gas that would have fueled new star formation has been used up or expelled or simply settled into a calmer state. Elliptical galaxies are in a sense the elder populations of the cosmic community, vast and luminous, but no longer in the active generative phase of their lives. Evidence suggests that many elliptical galaxies form through the merging of smaller galaxies, their original shapes dissolved and redistributed by the violence of collision into something rounder, something more diffuse. And then there are the irregular galaxies, the ones that fit neither category neatly. Asymmetrical, sometimes chaotic in appearance, often the result of gravitational interactions with neighbouring galaxies, that have distorted their original forms. The Large and Small Magellanic Clouds. Two small companion galaxies visible from the southern hemisphere with the naked eye are irregular in structure, shaped partly by their long gravitational relationship with the Milky Way, which has tugged at them repeatedly over billions of years and left its mark in their asymmetry. What we understand so far suggests that this variety spirals, ellipticals, irregulars, and the many gradations between them emerges from a relatively small set of underlying physical principles. Gravity, the conservation of angular momentum, the way gas cools and condenses into stars under the right conditions, the dynamics of dark matter which provides the scaffolding within which visible matter collects and organizes itself. These principles applied across the enormous variety of initial conditions present in the early universe have produced a cosmos filled with galaxies as diverse in their particulars as forests are diverse in their trees, each one shaped by the same fundamental processes but no two exactly alike. There is something in that diversity that invites a kind of quiet appreciation. The universe did not need to make so many different kinds. It did not need to produce ring galaxies or polar ring galaxies or galaxies with double nuclei or galaxies so diffuse they are barely distinguishable from the empty space around them. And yet it did, as though variety itself was somehow written into the initial conditions, as though the same basic rules given enough time and enough matter and enough space cannot help but proliferate into shapes and structures that no one could have predicted from the rules alone. Scientists suggest this is partly a consequence of the way complex systems behave. Simple rules iterated across vast scales and vast timescales tend to produce outcomes that are genuinely surprising. Not because the rules have been broken, but because the full implications of even simple rules are in practice inexhaustible. A galaxy is in some respects the universe thinking through the consequences of its own physics. For most of the history of astronomy, what we could observe about galaxies was limited by the sensitivity of our instruments. We could see the stars, the broad shapes, the general colour and luminosity. But the deeper structure, the distribution of mass, the behaviour of gas in the outer regions, the faint stellar populations at the edges remained largely invisible. It was as though we were looking at a painting from a great distance, able to make out the broad composition, but missing the finer details of brushwork and texture. What changed everything, or began to change it, was the discovery that galaxies contain far more mass than can be accounted for by their visible stars and gas. This realization came gradually through careful measurements of how stars at different distances from a galaxy's center were moving. According to the physics of gravity, stars further from the center of a galaxy should orbit more slowly, just as the outer planets of the solar system orbit the sun more slowly than the inner ones. But that is not what astronomers observed. The stars in the outer regions of galaxies were moving faster than they should have been given the amount of visible mass present. The most straightforward explanation, and the one that has over decades of increasingly precise observation become the dominant framework, is that galaxies are embedded within enormous halos of matter that does not emit or absorb light. Matter that interacts gravitationally with the visible galaxy, providing the extra mass needed to account for the observed stellar velocities, but which cannot itself be seen. This is what is known as dark matter. Not dark in the sense of malevolent or absent, but dark in the simple descriptive sense of not interacting with light. Studies indicate that dark matter constitutes approximately 85% of all the matter in the universe. The stars, the gas, the planets, every visible structure ever observed, all of that represents only about 15% of the total matter content. The rest is invisible to every instrument we have ever built, detectable only through its gravitational effects on the things we can see. It may be that this is the most fundamental revision in the history of astronomy, the recognition that what we can see is not most of what is there, that the universe in its material composition is overwhelmingly made of something we do not yet understand, something that holds galaxies together, shapes their formation, and yet has never been directly detected in any laboratory on Earth. The mind sitting with that fact quietly tends to find it not frightening, but strangely liberating. If most of the universe is still unknown, not merely undiscovered in its details but unknown in its basic nature, then the story of what the cosmos is made of is still in the most important sense incomplete. We're not at the end of understanding, we're in many ways still very near the beginning, and it is within this framework galaxies held together by invisible matter, shaped by forces both understood and not yet understood, spread across a universe far stranger in its composition than anyone expected, that the truly unusual galaxies become even more remarkable. Because they do not merely deviate from the visible pattern, they deviate from the invisible one as well. They exist in arrangements that challenge not only what we know about stars and gas, but what we think we know about dark matter itself. That tension between what the models predict and what the telescopes actually find is one of the quieter engines of modern astronomy. It does not announce itself loudly. It does not resolve in a single revelation. It accumulates slowly in the careful comparison of data and expectation, in the papers exchanged between researchers at institutions scattered across the world, in the late nights spent running simulations that keep producing the wrong answer, and somewhere in that accumulation, in that patient and unhurried process of revision, there is a galaxy that was discovered not because anyone was looking for something strange, but because the data examined carefully enough revealed something that simply should not have been there. It is large enough to have been visible all along, in a sense. It was the nature of what it was made of, or what it was not made of, that made it so difficult to recognize for what it was. The light it carries is faint. Faint enough that for years it blended into the background of deeper surveys, mistaken for something else, or simply overlooked in the way that the unfamiliar is so often overlooked, until someone develops the particular kind of attention required to see it. What scientists found when they finally looked carefully was a galaxy composed almost entirely of dark matter, with so few stars that it occupies the same volume as the Milky Way, while remaining nearly transparent to the eye. And the question it raised when it was finally understood for what it was, is one that is still being quietly turned over in the minds of astronomers who have spent years thinking about how galaxies form and what they are made of. How does something so large become so empty, and what does its existence tell us about the parts of the universe we will never be able to see? There is a particular kind of discovery that does not arrive with noise. It does not announce itself in a press release or interrupt the ordinary rhythm of a research day with sudden clarity. It arrives quietly the way certain realizations do, as a small irregularity in data that someone on a particular afternoon happened to look at a little more carefully than usual, and in looking carefully found that the irregularity was not a mistake, it was a galaxy. The object now known as Dragonfly 44 was identified in the year 2015 as part of a survey conducted using a telescope specifically designed to detect faint low surface brightness objects. The Dragonfly telephoto array is not by the standards of modern astronomy a large instrument. It was built from a modest collection of telephoto camera lenses, the kind used in sports photography, arranged together and pointed at the sky. Its strength is not magnification, but sensitivity. Its ability to gather the faintest whispers of light from objects that brighter, more powerful telescopes tend to simply overlook. What it found in a region of sky within the Coma Galaxy cluster was something that required several follow-up observations before astronomers were confident they understood what they were seeing. Dragonfly 44 is in terms of its overall size roughly comparable to the Milky Way. It occupies a similar volume of space. It is not a small object, and yet when researchers turned more powerful instruments toward it to measure how many stars it contained, the number they found was startlingly low. Approximately 1/100% of the stellar population of the Milky Way, a galaxy the size of our own containing almost nothing that can be seen. Evidence suggests that the total visible mass of Dragonfly 44, all its stars combined, accounts for less than 1% of the total mass needed to explain the galaxy's behavior. The stars that are there move far too quickly. They are orbiting rotating holding formation in ways that require far more gravitational pull than their combined light could ever produce. Something else must be providing that pull, something present in overwhelming proportion and entirely invisible. Dark matter, by current estimates, comprises approximately 99.9% of this galaxy's total mass. It is in the most literal physical sense a ghost galaxy, a vast and patient structure of invisible matter, wearing only the faintest costume of visible stars. Fewer than 1 billion stars spread across a volume that should, by the logic of ordinary galaxy formation, contain hundreds of billions. Scientists are still exploring exactly how such an object comes to exist. The leading hypotheses involve the galaxy's location within the Coma Cluster, one of the densest collections of galaxies known a region, where gravitational tidal forces are strong, where galaxies interact and strip material from one another over long timescales. It may be that Dragonfly 44 was once a more conventional galaxy, one that began forming in a normal way, accumulating gas and building stars, but that repeated gravitational encounters with its neighbours stripped away much of the ordinary matter before it could fully develop. What remained was the dark matter halo, which is more gravitationally bound and harder to remove, now containing only the sparse stellar population that managed to form before the rest was pulled away. There is something in this image worth sitting with for a moment. A galaxy that was in some sense interrupted, that began the slow process of becoming something fuller, something more luminous, and then had that process arrested by the gravitational presence of its surroundings. The matter that would have become stars was pulled elsewhere. The framework remained, and within that framework, held together by invisible mass across hundreds of millions of years, a small population of stars continues to orbit unaware, in whatever sense stars can be said to be unaware of anything of how much was missing. What we understand so far suggests that Dragonfly 44 is not unique. Since its discovery, surveys using similar low-surface brightness techniques have identified hundreds of ultra-diffuse galaxies objects that share its general character, if not always its extreme dark matter fraction. The Coma Cluster alone appears to contain more than 800 of them. They were always there. The instruments capable of seeing them simply did not exist, or were not looking in the right way. This is a pattern that recurs throughout the history of astronomy. Not that the universe withholds its stranger contents deliberately, but that each generation of instruments reveals a layer of reality that the previous generation could not access. And each new layer tends to be in some way unexpected. The universe does not appear to run out of things that behave differently than anticipated. The discovery of ultra-diffuse galaxies as a population has complicated the existing models of galaxy formation in ways that researchers are still working through. The models had in general predicted that dark matter, halos of a certain mass, would produce galaxies of a certain stellar content. The prediction was derived from simulations from enormous computational models of how the universe evolves, run on some of the most powerful computers available. These simulations are sophisticated, carefully calibrated, and in many respects remarkably successful at reproducing the large-scale structure of the cosmos, And yet when objects like Dragonfly 44 began appearing in observational data with regularity, the simulations had difficulty accounting for them. Not because the physics was necessarily wrong, but because the specific combination of conditions required to produce a galaxy so dominated by dark matter was either rare in the simulations or required adjustments to parameters that were not well constrained. It may be that the models will eventually be refined to accommodate these objects naturally, or it may be that they are pointing towards something in the behavior of dark matter itself that current models do not fully capture. What the mind tends to find curious sitting with this particular galaxy is not the strangeness of the dark matter fraction alone, but the question of what it means for a galaxy to be almost entirely invisible. We speak of galaxies as luminous objects, as the lights in the darkness of intergalactic space, the structures we use to map the universe, the sources of the photons that travel across billions of light years to reach our instruments. But Dragonfly 44 is a reminder that the luminous part of the universe is in a sense a surface detail, a thin film of visible activity resting on top of a much larger, much more massive substrate that neither glows nor reflects nor absorbs in any way we can directly measure. It seems that if you were somehow transported to the interior of Dragonfly 44, placed somewhere within its volume at locations similar to where the Sun sits within the Milky Way, the sky around you would be strikingly empty by the standards of our own galaxy. Instead of the dense band of the Milky Way stretching across the night, you would see only a sparse scattering of distant suns. The space between them would be vast. The darkness would be in some directions almost total, and yet you would be inside a galaxy surrounded by more mass than you could ever calculate, all of it invisible, all of it present, holding the whole thin structure together with a gravity so quiet it makes no sound and casts no light. There is a quality to that image of immense presence without visibility that the mind registers in a particular way, as though some part of our intuition about what it means for something to be there, to be real, to occupy space and matter in the world is being gently revised. Researchers have found in the year since Dragonfly 44's discovery that the study of ultra-diffuse galaxies has become one of the more active areas of observational cosmology. Not because these objects are the most dramatic, but because they occupy a strange edge of the possible region of parameter space, where ordinary galaxy physics seems to have taken an unusual turn, and where the behavior of dark matter can be examined in conditions that are in some ways more extreme than in ordinary galaxies. They are in their quietness and their sparseness particularly useful, precisely because so much of the usual noise has been removed. There are also ultra-diffuse galaxies that complicate the picture in a different direction. In the year 2018, a galaxy designated NG-C1052-DF2, a name less poetic than Dragonfly 44 but equally strange in its implications, was reported to contain almost no dark matter at all. Where Dragonfly 44 is nearly all dark matter, this galaxy appeared to be nearly all ordinary matter. The dark matter fraction was so low as to be within the margin of observational uncertainty essentially absent. Studies indicate that this finding was controversial from the moment of its publication, and subsequent observations have produced somewhat different results. The current picture remains uncertain, with some analyses suggesting a small but non-negligible dark matter component, others continuing to find less than expected. But the central observation that some galaxies appear to contain dramatically less dark matter than standard formation models would predict has been confirmed in a small number of other ultra-diffuse objects as well. The implication, if these observations are correct, is that dark matter and ordinary matter can be separated from one another to a degree that standard models did not anticipate. that it is possible under the right conditions for a galaxy to form and persist with very little of the invisible scaffolding that we'd come to think of as essential, which raises in turn the possibility that the relationship between dark matter and the visible universe is more variable, more contingent, more sensitive to local conditions than the broad brush picture had suggested. It is a kind of loosening, a recognition that the rules, wherever they are still being written, have more flexibility in them than anyone initially supposed. And what scientists discovered when they turned their attention to the oldest light in the universe, to the galaxies that formed not in the recent cosmic past but in the very earliest chapters of time, is something that deepens this sense of loosening still further. Because the strangeness of galaxies like Dragonfly 44 is in some respects a strangeness of composition. But what the deepest surveys have revealed is a different kind of strangeness altogether. A strangeness not of what galaxies are made of, but of when they are. And what was found there in the light from the universe's earliest ages is something that the models had quietly predicted would not exist, and yet does. The universe has a beginning. Not in the philosophical sense, not as a matter of belief or cosmological preference, but as a measurable, observable fact. Approximately 13.8 billion years ago, everything that exists, all the matter, all the energy, all the space itself emerged from a state of extraordinary density and temperature and began expanding. That expansion has never stopped. The universe has been growing, cooling, and complexifying ever since. In the very earliest moments there were no stars, no galaxies, no planets, no atoms heavier than hydrogen and helium, no structures of any kind beyond the faint ripples of density variation that had been seeded into the fabric of space itself. Everything that exists today, every mountain, every ocean, every galaxy visible in the deepest survey images grew from those ripples through the patient incremental action of gravity over billions of years. This is the standard picture, and it is in its broad outlines extraordinarily well supported. The evidence for it comes from multiple independent sources from the cosmic microwave background radiation, which is the faint afterglow of the early universe still detectable in every direction of the sky. From the observed abundance of light elements which matches the predictions of early universe nuclear synthesis with remarkable precision. From the large-scale structure of the galaxy distribution, which bears the imprint of those original density fluctuations amplified across cosmic time. It is one of the great achievements of modern science, a coherent evidence-based narrative of cosmic history, stretching from the first fractions of a second to the present day, and it makes certain predictions about what the early universe should have looked like, about what kinds of structures should have existed at different points in cosmic history, about how long it takes given the physics of gravity and gas cooling and dark matter collapse for a galaxy to grow from a small initial overdensity into something large, massive and settled. Those predictions, it turns out, have been having a difficult few years. The James Webb Space Telescope, which reached its operational position approximately 1,500,000 kilometers from Earth in the early part of this decade, was designed in part to look further back in cosmic time than any previous instrument. Its infrared sensitivity allows it to detect the light from objects so distant and therefore so ancient that the expansion of the universe has stretched their originally visible light into wavelengths far beyond what the human eye can see. By gathering this stretched ancient light, the telescope can observe the universe as it existed within the first few 100 million years after its beginning. What researchers have found in that ancient light has been in the measured language of scientific papers surprising. In the more candid language of conference discussions, it has been for some cosmologists genuinely unsettling. There are galaxies out there observed in the earliest epochs that current telescopes can access that are too massive, too mature, too settled and fully formed for objects that should, according to the standard model of galaxy formation, still be in their infancy. Galaxies that appear to contain hundreds of billions of solar masses of stars, organized into stable structured systems at a point in cosmic history when the universe was less than 1 billion years old. Some of the candidates identified in early Webb observations appear to have formed the equivalent of 1 trillion solar masses of stars in the first few 100 million years, a rate of star formation so rapid that current models struggle to accommodate it. It may be that some of these extreme objects will on further analysis turn out to be somewhat less massive than initial estimates suggested. Measuring the mass of a very distant galaxy is technically demanding, and early measurements sometimes require revision as better data becomes available. Scientists are still exploring the full range of these objects and refining the techniques used to characterize them, but even accounting for observational uncertainty, the emerging picture is clear enough to have generated serious scientific discussion about what it means. The galaxies that should not yet exist, the ones that were somehow already old when the universe was still very young, are appearing with enough regularity to suggest that something in the standard formation timeline may need to be revisited. There is a particular category of these anomalously mature objects sometimes called red and dead galaxies. The term is descriptive rather than poetic red, because the light they emit is dominated by older, cooler stars rather than the blue-white light of young, hot star-forming regions. Dead in the sense that star formation within them has essentially ceased. They have used up expelled or otherwise lost access to the gas that would have fueled continued stellar birth. They are in their internal dynamics quiet. What makes them strange is not their quietness per se. Elliptical galaxies in the present-day universe are often similarly quiescent. What makes them strange is when they are quiet. Evidence suggests that some of these red and dead galaxies completed the bulk of their star formation within the first billion years of cosmic history, and then simply stopped. While the universe around them was still actively building new structures, still assembling larger and larger complexes of matter, these galaxies had already run through their entire star-forming phase and entered a kind of premature senescence. The question of what quenched them, what shut off the star formation so early and so completely, is one that researchers are actively working on. Several mechanisms have been proposed. One involves the supermassive black holes that appear to reside at the centers of most large galaxies, as these black holes grow through the accumulation of infalling matter. They release enormous amounts of energy in the form of jets and radiation, which can heat the surrounding gas and prevent it from cooling to the point where new stars can form. This process, known as feedback, is thought to play an important role in regulating star formation in galaxies generally. But producing the extreme early quenching observed in these objects may require either unusually massive black holes forming very early, or a feedback mechanism more efficient than current models predict. Another possibility involves the environment. Some of the most massive early galaxies appear to have formed in particularly dense regions of the early universe regions, where the rate of galaxy interactions and mergers was high. Studies indicate that the violence of repeated mergers can under certain conditions simultaneously trigger intense bursts of star formation that rapidly exhaust available gas and generate feedback powerful enough to expel what remains. The result is a galaxy that forms enormous numbers of stars in a very short time geologically speaking, and then has nothing left to form stars with. What we understand so far suggests that both mechanisms are likely operating perhaps in different proportions in different objects, perhaps in concert. The universe does not appear to have used a single recipe. There is something worth pausing over in the image of a galaxy that ages too quickly. We carry in ordinary life an intuition about time and maturity that runs roughly as follows. Things that are old have had time to develop. They have passed through earlier, simpler stages on the way to whatever complexity they currently exhibit. Age implies history, and history implies duration. But these early galaxies seem to compress that history into a span of time that by cosmic standards is almost startlingly brief. 1 billion years sounds enormous to human ears. Against a universe that is nearly 14 billion years old, it represents the first 7% of all of cosmic time. The equivalent, if you mapped the age of the universe onto a single human year, of having fully matured by the 3rd week of January. The mind quietly registers this as a kind of inversion, a reversal of the expected relationship between age and development, and it opens a question that does not resolve quickly about whether the early universe, for reasons not yet fully understood, was somehow more efficient at building complexity than the universe is today. Whether the conditions present in those earliest epochs, higher density, more frequent interactions, different temperatures and timescales, produce something like an accelerated version of the processes that now unfold more slowly. It may be that the universe had in its youth a kind of intensity it has since lost, the way certain early mornings have a quality of light that does not last clear and sharp and briefly extraordinary before settling into the ordinary texture of the day. Researchers have found in examining the stellar populations of these early massive galaxies that their stars tend to contain higher concentrations of heavy elements than might be expected for objects that formed so early. Heavy elements, everything beyond hydrogen, helium and lithium, are produced inside stars and released when stars die. The first stars in the universe formed from almost pure hydrogen and helium. The heavy elements that exist today accumulated gradually over many stellar generations as successive waves of stars were born, lived and died. The presence of elevated heavy element concentrations in very early galaxies implies that even before these galaxies are observed, they had already cycled through at least one, possibly several generations of stellar birth and death. Even the stars we can see in these ancient systems are not the first ones. The first ones have already come and gone. It seems that the earliest chapters of the universe were busier than anyone expected. Fuller, more rapid in their cycling through the phases of stellar life, as though time itself in those first hundreds of millions of years was running faster, not literally, but in terms of the density of events compressed into each successive interval. The James Webb Space Telescope continues to accumulate data. Each observing cycle adds new objects, new measurements, new candidates for the category of things that should not yet exist. And with each addition, the theoretical picture shifts a little further from its original shape, not collapsing, not invalidated, but stretching at its edges, accommodating slowly and carefully the evidence of a universe that is in its early history more surprising than anyone modelled. Some of the galaxies being found at these extreme distances are not merely old, they are also in certain cases structured in ways that were not expected to develop until much later, with disk-like geometries, with organised rotation with the internal architecture that in the present-day universe takes billions of years to settle into stability. What that means for the full picture of how structure forms in the universe is still being worked out. It is one of those scientific situations where the answer, whatever it turns out to be, will require absorbing a genuinely new idea about how things happen. Not a small correction, a real revision, and somewhere in that revision, in the slow, careful work of reconciling what the models predicted with what the telescopes have actually found, there is a quieter question waiting. Not about when these galaxies formed or how quickly, but about what their existence implies for the structures we have never yet observed at all, the ones that do not announce themselves in starlight, the ones whose presence is felt only in the way other things move around them. What was found in those spaces between visible structures is something the universe may have been arranging all along in the patient and unhurried way that only becomes visible when you learn how to look for absence rather than light. There is a particular kind of beauty that only becomes visible after something has already passed through. Not the beauty of arrival or of presence, but of aftermath. The way a stone dropped into still water leaves a ring that travels outward long after the stone itself has settled to the bottom. The way a forest decades after a fire shows the shape of what the fire did not in destruction, but in the particular arrangement of what grew back and where and in what order. The universe makes this kind of beauty too, and some of its most striking examples are not the result of slow, patient accumulation, but of collision of one enormous thing passing directly through another and leaving behind in the long silence that follows a shape that should not be possible by any ordinary measure of how galaxies are supposed to behave. The Cartwheel Galaxy sits approximately 500 million light-years away in the constellation Sculptor. It was first identified in ground-based surveys as an unusual object, a galaxy with a bright, compact central region surrounded by an enormous outer ring, the two connected by a series of faint spokes radiating outward like the wheel of a bicycle. The name came easily, the shape was unmistakable. What was less immediately clear was how such a shape had come to exist. Researchers have found through decades of observation and increasingly detailed computer modelling that the cartwheel is the result of a direct collision. Somewhere between 200 million and 300 million years ago, a smaller galaxy passed almost straight through the centre of what was at that time a relatively ordinary spiral galaxy, moving not alongside it, not in a grazing encounter, but through it like a bullet passing through still water, along an axis very nearly perpendicular to the plane of the disk. The effect of that passage was not what intuition might suggest. In everyday experience, when one solid object passes through another, there is impact fracture, the kind of damage that follows from physical contact. But galaxies are not in the relevant sense solid. The distance between individual stars within a galaxy is so vast that two galaxies can pass through one another without a single stellar collision occurring. What interacts is not the stars themselves, but the gravitational field and the gas. As the smaller galaxy referred to in the literature as the bullet for clarity passed through the centre of the larger one, its gravitational influence sent a wave of compression rippling outward through the disk, a circular wave expanding concentrically from the point of impact, pushing gas and dust ahead of it as it travelled. And where gas compresses sufficiently, conditions become favourable for the formation of new stars. The wave, as it travelled outward, left behind it a ring of newly formed stars, young, hot, intensely luminous, that is now visible as the brilliant outer structure of the cartwheel. It seems that this process, a ring wave of star formation propagating outward from a central impact, is not unique to the cartwheel. Evidence suggests that other so-called ring galaxies share a similar origin story. The Hoag's object, a nearly perfect ring of blue stars surrounding a central yellow nucleus, with almost nothing in between, is thought by many researchers to have formed through a related mechanism, though the details of its particular history remain somewhat uncertain. The Lindsay-Shapley ring, the AM0644-741, each of these unusual structures carries the signature of something that passed through. The mind quietly registers a certain quality in this kind of formation. The idea that what looks like a deliberate, almost geometric pattern, a perfect ring, clean and symmetrical against the darkness of space, is not the product of careful construction, but of a single brief violent event that happened hundreds of millions of years ago and has been slowly expressing its consequences ever since. The ring is not the collision. The ring is the memory of the collision still travelling outward. At the current rate of expansion, the outer ring of the cartwheel is moving away from the galactic centre at approximately 100 kilometers per second. it has already travelled to a radius of approximately 150,000 light-years larger than the Milky Way. The wave of star formation it carries has produced stars that live fast and die young, burning bright in blue and ultraviolet light before exhausting their fuel in a matter of millions of years. These are not stars built for longevity. They are stars built for intensity. Brief, brilliant presences in a ring that will continue to expand until the density wave dissipates and the trigger for new formation fades. Behind the wave, the gas it compressed has been partially used up. Studies indicate that the inner regions of the cartwheel show a different character than the outer ring, older stellar population's less active star formation, the quieter texture of a place that was already settled before the wave passed through and the wave has now moved beyond. There is an archaeology to it if one looks carefully, a record of the wave's passage written in the age and distribution of stars at different radial distances from the centre. What we understand so far suggests that the smaller galaxy responsible for the cartwheel's transformation is now located some distance from the collision site. It continued moving after the impact carried by its own momentum. Identifying the culprit with certainty is complicated by the fact that several small galaxies in the vicinity are potential candidates, and reconstructing the precise geometry of a collision that happened hundreds of millions of years ago requires careful modelling of orbits and gravitational histories. But the broad geometry is clear enough. Something came from above or below the disk, passed through it, and left a ring that is still hundreds of millions of years later, expanding outward in silence. There is something in the scale of these timescales that the human mind tends to approach obliquely, as though looking directly at it would be too much. Hundreds of millions of years, a wave of star formation travelling at 100 kilometers per second and yet requiring hundreds of millions of years to reach its current extent. The bullet galaxy still moving away from the collision site, but slowly enough and far enough that its path is only reconstructible through inference and modelling rather than direct observation. Time in cosmology behaves differently than the word suggests in ordinary use. It is not simply the accumulation of moments, it is the medium through which processes of unimaginable scale express themselves slowly, continuously in ways that only become legible when you step back far enough to see the full arc of the consequence. It may be that this is one of the stranger gifts that astronomy offers, if gift is the right word. The ability to look at an object, a ring of stars, a disrupted spiral, a trail of debris stretched between two merging galaxies, and understand that what you are seeing is not the event itself, but its echo. That the actual moment of impact, of collision, of disruption happened so long ago that the universe has had time to evolve considerably since then, and yet the echo's still there, still visible, still carrying information about what occurred in the moment that created it. Scientists suggest this is part of what makes ring galaxies particularly valuable as objects of study. They are in a sense time capsules, objects whose current appearance encodes information about a specific datable event in their past, and whose ongoing evolution can be used to test models of how galaxies respond to perturbation. By comparing different ring galaxies at different stages of their post-collision evolution, researchers can in effect construct a timeline of how the ring wave develops peaks and eventually dissipates, a timeline that would be impossible to observe in any single object over the span of a human lifetime, but which becomes accessible when many objects at different points in the same process are compared simultaneously. It is a technique that recurs throughout observational astronomy, this use of populations to reconstruct histories. Because no human lifespan, no instrument built by human hands can observe a single galaxy through its full evolutionary arc, the science proceeds by finding many galaxies in different states and assembling their individual snapshots into a coherent sequence. The history of the cosmos is read not through continuous observation, but through comparative inference, the same way a geologist reads the history of a landscape from the layers of rock exposed in a cliff face, each layer a frozen moment in a process that unfolded over timescales no individual witness could encompass. Researchers have found that the cartwheel specifically has been observed at multiple wavelengths over the past several decades from radio to X-ray, and each wavelength reveals a different aspect of its structure. In X-ray light, the ring glows with the emission of supernovae and neutron stars, the death echoes of massive stars that formed in the ring wave and have already completed their brief lives. In radio wavelengths, the distribution of neutral hydrogen gas reveals the dynamics of the expanding structure. In the infrared, the warm dust heated by embedded stars traces the sites of ongoing formation. Layered together, these observations produce a picture of a galaxy that is in a very real sense still in the process of recovering from something that happened to it hundreds of millions of years ago. Recovery is perhaps not quite the right word. Transformation is closer. The cartwheel that existed before the collision is gone. The cartwheel that exists now is a different object shaped by what happened to it, carrying in its structure the permanent record of an event it cannot, of course, remember, but whose consequences are written into the arrangement of every star and cloud of gas within its boundaries. The universe, it turns out, does not simply accumulate structure. It disrupts it, reshapes it, sends waves through it, and then watches in the patient indifferent way of physical processes as the structure reorganizes itself around the memory of the disruption. And the rings that result from this reorganization are in their own way among the most honest structures in the cosmos. They do not disguise their history. They wear it visibly expanding, luminous, still in motion, as though the event that created them is not yet quite finished expressing itself. What comes into view when the gaze moves from these bright disruptive rings toward the quieter edges of the galaxy population is something almost opposite in character. Not the aftermath of collision, not the visible record of something that passed through, but an object so dispersed, so gently spread across space, that it seems to have been arranged by something more like a slow exhale than an impact. Something pulled apart so carefully over such a long time that what remains is less a galaxy than a suggestion of one. There is a threshold in the natural world beyond which something becomes difficult to name. A fog is still a fog even when it thins to the point where you can see through it clearly. A sound is still a sound even when it fades to the edge of what the ear can detect. But at some point the thinning becomes significant enough that the category itself begins to feel uncertain. You're not sure anymore whether what you are experiencing deserves the same word as what it was when it was denser, more present, more unambiguously itself. Astronomers have encountered this problem with a class of galaxies that sit at the very edge of what the word galaxy can comfortably contain. They're called ultra-diffuse galaxies, a term that arrived in the scientific literature with something close to descriptive precision. Ultra meaning extreme, diffuse meaning spread out low in density thin. These are objects that occupy the same volume of space as large ordinary galaxies, in some cases volumes comparable to the Milky Way, but which contain so few stars and distribute those stars so sparsely across that volume that the surface brightness of their visible light is only a small fraction of what even the faintest conventional galaxies display. To put it another way, if you could somehow travel to one of these galaxies and look at it from within, the sky around you would be darker than the sky inside the Milky Way. Far darker. The stars would be there, but they would be separated from one another by distances so vast that the collective glow of the galaxy would not be distinguishable from the general background light of the universe itself. You would be inside something in a gravitational and structural sense without being able to tell that you were inside anything at all. Researchers have found that ultra-diffuse galaxies are not rare. They appear in large numbers in galaxy clusters, those dense environments, where hundreds or thousands of galaxies occupy a relatively small region of space, bound together by their collective gravity. The Coma cluster, which we touched on earlier in connection with Dragonfly 44, contains hundreds of them. The Virgo cluster, the nearest large galaxy cluster to the Milky Way, contains similar numbers. It may be that virtually every large galaxy cluster is surrounded by a population of ultra-diffuse objects that previous surveys lacking the sensitivity to detect such faint surface brightnesses simply missed entirely. The question of how they form is one that scientists are still exploring, and the answer may not be singular. There appear to be at least two distinct formation pathways producing objects that look superficially similar, but arrived at their current state through very different histories. The first pathway involves the tidal forces of the cluster environment itself. When a galaxy falls into a massive cluster, the gravitational field of the cluster does not pull on it uniformly. The side of the galaxy facing the cluster center is pulled more strongly than the side facing away. This difference, what physicists call a tidal force, stretches the galaxy along the direction of its motion, and over many billions of years can pull its stars into long, diffuse streams, redistributing them across a much larger volume than the galaxy originally occupied. The result is an object that has been, in a quite literal sense, stretched by the gravitational environment it moved through. Evidence suggests this mechanism is particularly effective for galaxies that entered the cluster on orbits that brought them close to the cluster center, where the tidal field is most intense. The second pathway is more intrinsic, rooted not in the environment, but in the galaxy's own initial conditions. Some ultra-diffuse galaxies appear to have formed from gas clouds that, for reasons related to their early angular momentum, expanded into unusually large, diffuse configurations rather than collapsing into the compact, dense structures that most galaxies develop. If the initial gas cloud was spinning relatively rapidly, the centrifugal effect of that rotation could have resisted the inward pull of gravity just enough to produce a system that stabilized at a much lower density than typical. The stars that formed from this diffuse gas were then spread from the very beginning across an unusually large volume. What we understand so far suggests that these two pathways produce populations that, while visually similar, differ in their internal properties in ways that careful observation can sometimes distinguish. Tidally stripped ultra-diffuse galaxies tend to show elongated shapes, aligned with the direction of the tidal force that stretched them, a geometric record of the process that created them. Those formed from high angular momentum gas tend to be rounder, more symmetric with no preferred orientation. The shape of a galaxy, when examined with sufficient care, can speak to its history in ways that straightforward brightness measurements alone cannot reveal. It seems that the internal dynamics of ultra-diffuse galaxies also carry diagnostic information. Some are rich in dark matter, in the manner of Dragonfly 44, their sparse stellar populations embedded within halos of invisible mass, far more extensive than the visible galaxy. Others puzzlingly appear to contain much less dark matter than expected objects whose total mass is dominated by the stars themselves without the usual invisible scaffolding. This range of dark matter, fractions from extreme excess to apparent deficit within a single morphological category, suggests that ultra-diffuse galaxies are not a coherent class defined by a single physical property, but rather a region of galaxy parameter space that multiple different formation pathways can arrive at by different routes. The mind tends to find this kind of convergence, multiple roads leading to the same apparent destination, quietly interesting. It is a pattern that recurs throughout natural systems, Different initial conditions, different environmental histories, different physical processes, all capable of producing objects that observed from a sufficient distance look very much alike. The superficial similarity conceals a deeper heterogeneity. The category on closer inspection turns out to be a collection of different things that happen to resemble each other at low resolution. Studies indicate that the stellar populations within ultra-diffuse galaxies tend to be old. Most of their stars formed long ago, in many cases in the first few billion years of cosmic history, and the galaxies have not formed significant numbers of new stars since then. This quiescence is consistent with both formation pathways. Tidally stripped galaxies lose the gas that would fuel new star formation as part of the stripping process, while high-spin galaxies may have used up their gas early in a brief initial burst and then had no mechanism to accrete fresh material from outside. There is something in the quality of this age that deserves a moment of attention. The stars in an ultra-diffuse galaxy are in many cases older than the Sun, older than the Earth. Formed in the dense, active early universe, they have been drifting through enormous volumes of space ever since spreading further from their neighbours, with each passing billion years as the galaxy slowly expanded or was gradually diluted by tidal forces. They've been travelling together in a loose and patient gravitational family for an immense span of time. The fact that the galaxy they comprise is nearly invisible does not diminish the antiquity of the individual stars within it. Each one is a record of an earlier epoch, carrying in its chemical composition the signature of the gas cloud from which it condensed, a gas cloud that no longer exists in any recognizable form, dissolved long ago into the general medium of space. Researchers have found that studying the chemical compositions of stars in ultra-diffuse galaxies, a technically demanding task given how faint these objects are, provides information about the history of star formation in the early universe that is difficult to obtain from other sources. Because these galaxies stopped forming stars so long ago, and have been largely isolated from the enrichment processes that have continued in more active galaxies, their stellar populations preserve a kind of chemical fossil record. They are in a sense windows into an earlier version of the universe, one in which the heavy elements we now take for granted were still accumulating in the interstellar medium, and in which the conditions for life as we understand it were in many places not yet fully established. It may be that the most philosophically striking thing about ultra-diffuse galaxies is not their scale or their dark matter content, or even the puzzle of their formation. It is the simple fact that they exist in such large numbers, have existed for such a long time, and were essentially unknown to science until very recently. The surveys that identified them in their hundreds and thousands were conducted within the last decade. Before that, the instruments existed, the regions of sky had been observed, but the particular combination of sensitivity and technique required to detect objects of such low surface brightness simply was not in place. There is a recurring lesson in this one that the history of astronomy keeps offering in different forms. The universe is not stingy with its contents. It does not hide things in the sense of concealing them deliberately. But it does require a certain quality of attention, a willingness to build instruments capable of detecting the very faint to look at regions of sky that have already been observed, but perhaps not in quite the right way, to revisit assumptions about what kinds of objects can exist and in what proportions. What we understand so far suggests that the full census of the universe's structures is still far from complete. The ultra-diffuse galaxies are in a sense a reminder of that incompleteness, a population hiding in plain sight, awaiting only the particular quality of attention required to bring them into focus. And if entire classes of galaxies containing collectively enormous numbers of ancient stars could remain overlooked for so long, it becomes reasonable to wonder what else might be present in the spaces between the structures we've already catalogued. The universe rewards, it seems, a certain patient thoroughness, a willingness to keep looking at places that seem already understood, with instruments a little more sensitive than the ones used before. Because the edge of what is known has a way of dissolving when approached carefully enough, giving way not to emptiness but to more. And the more in this case is not always dramatic, not always bright or violent or easily named. Sometimes it is quiet and sparse and nearly transparent, much like what happens in certain late hours when the mind itself begins to thin at its edges, not losing anything but releasing the density of ordinary thought, spreading outward into something larger and less defined. There is a quieter layer to all of this, one that most people never consider about what it means when a galaxy's very center holds not one heart, but two, slowly drawing toward each other across a distance measured in light years, in a kind of convergence so gradual it cannot be hurried and cannot be stopped. Some things move toward each other so slowly that the motion itself is almost indistinguishable from stillness, not because nothing is happening, but because what is happening unfolds across timescales so vast that the word movement loses its ordinary meaning, the way a glacier moves technically, but not in any sense that a single, watching life could register. The motion is real. The direction is set. The outcome is, in the patient language of gravitational physics, essentially inevitable. It is simply that the interval between now and the moment of completion is longer than everything that has existed so far. There are galaxies in the universe that contain at their centers not one supermassive black hole but two enormously massive, extraordinarily compact objects, each occupying the same general region of the same galaxy, each influencing the other through gravity, and each very slowly spiraling inward toward the other across a distance that diminishes by an imperceptible amount each year, but diminishes nonetheless, following a path whose endpoint is a merger so energetic that it would release in the moment of coalescence more power than the combined light output of every star in the observable universe. That endpoint is still millions or hundreds of millions of years away in most of the dual black hole systems currently known. We're in observing them watching the beginning of a process whose conclusion we will never see. But the beginning itself is visible, and what it reveals about the lives of galaxies, about how they grow, how they merge, and what happens to the structures at their centers when two become one, is one of the more quietly extraordinary chapters in modern astrophysics. To understand how a galaxy comes to have two central black holes, it helps to consider the broader context of galaxy mergers. Researchers have found that galaxy mergers are not rare catastrophic events. They are a normal part of the evolutionary history of large galaxies. The universe is filled with galaxies moving through space, drawn together by gravity approaching one another across billions of years of cosmic time, and when two galaxies come close enough, their gravitational interaction begins a process that may eventually result in their combination into a single larger system. The Milky Way itself is the product of many such mergers. Evidence preserved in the motions and chemical compositions of stars in different regions of our galaxy suggests that the Milky Way has absorbed numerous smaller galaxies throughout its history, swallowing them, redistributing their stars throughout its own structure, and incorporating their material into the disk, the halo, and the bulge. The Sagittarius dwarf galaxy is currently in the process of being disrupted and absorbed. The Large Magellanic Cloud scientists suggest may eventually follow on a timescale of billions of years. When two large galaxies merge, galaxies comparable in mass to the Milky Way, the process is neither instantaneous nor smooth. The two systems first pass through one another, then separate, then fall back together, executing a series of orbiting encounters over hundreds of millions of years before finally settling into a single combined structure. During this process, the stars of both galaxies are redistributed through gravitational interactions, their orbits scrambled and reordered into new configurations. Gas is compressed, triggering intense bursts of star formation. The overall shape of the combined system is transformed, often losing any resemblance to the original spirals that contributed to it, and emerging as something rounder, more elliptical, more settled. And at the centers of these merging systems, the supermassive black holes that originally resided at the hearts of each individual galaxy find themselves eventually within the same galaxy. Separated initially by tens of thousands of light years, the scale of the galaxies themselves, but bound to each other by gravity, and committed by the physics of their situation to a slow approach. What we understand so far suggests that the journey from widely separated to closely orbiting is not simple. In the early stages of the merger, when the two black holes are still separated by thousands of light years, dynamical friction, the drag exerted on each black hole by the stars and gas through which it moves, causes them to lose energy and sink toward the common center of the merged galaxy. This process is relatively well understood and proceeds on timescales of a few billion years. But as the separation decreases below roughly a few light years, a problem emerges. At these smaller separations, the pool of stars whose orbits intersect the black hole binary, and can therefore carry away the angular momentum that the binary needs to lose in order to continue shrinking, begins to be depleted. Each star that passes close to the binary is flung away at high velocity, and the supply of stars on suitable orbits diminishes. In the absence of a mechanism to replenish that supply, the binary may stall at this separation, not merging, not separating, simply orbiting at the same distance indefinitely. This problem has a name in the literature: the final parsec problem. It refers to the difficulty of closing the last unit of separation, approximately 3.2 light years, between two massive black holes that have already come a very long way toward each other. The parsec itself is simply a unit of astronomical distance, but it's taken on a certain weight in discussions of binary black hole evolution, as the name for a gap that existing theories do not always bridge cleanly. Scientists are still exploring what resolves this problem in practice. Several mechanisms have been proposed. Non-spherical distributions of stars in the merged galaxy's center can continuously refill the loss cone, the region of orbital space from which stars interact with the binary, by scattering stars into suitable orbits through collective gravitational effects. Gas dynamics may play a role, with accreting gas transferring angular momentum away from the binary and allowing it to continue shrinking. And in galaxies undergoing ongoing minor mergers or accretion events, the continuous perturbation of stellar orbits may maintain an adequate supply of stars to drive the binary's evolution. It may be that the final parsec problem is in most real galaxies less of a barrier than the theoretical formulation suggests, that the idealized conditions under which it becomes severe are rarely realized in the messy, asymmetric, gas-rich environments of actual post-merger galaxies. The detections of gravitational wave signals consistent with merging black holes, announced over the last decade by ground-based detectors sensitive to stellar mass black holes, suggest that the coalescence problem is solvable at those smaller scales. The equivalent question for supermassive black holes, the kind residing at galaxy centers, awaits data from space-based gravitational wave detectors still in development. The most compelling evidence for dual supermassive black holes in a single galaxy comes from objects known as dual active galactic nuclei systems, in which both black holes are actively accreting material and are therefore visible as two distinct bright sources within the same galactic system. When a black hole is actively accreting, it generates an enormous release of energy, sometimes outshining the entire surrounding galaxy by a factor of hundreds or thousands in a phenomenon known as a quasar or active galactic nucleus. Two such objects visible within the same galaxy, moving at velocities consistent with mutual orbital motion, provide strong evidence for a genuine binary system. Researchers have found several confirmed examples of dual active galactic nuclei, and a considerably larger population of candidates awaiting detailed follow-up observations. The separations in confirmed systems range from tens of thousands of light-years to sub-parsec scales detectable only through very precise measurements of how the emission lines in their spectra shift back and forth as the two objects orbit each other. At these small separations, the orbital periods are short enough years to decades that the motion can be tracked in real time over the span of a research career. There is something specific about the quality of attention required to study these systems. The knowledge that what you are measuring is a motion that will continue long after every instrument involved has been decommissioned, long after the scientists conducting the measurement have lived their full lives. The data point you collect today is one sample from an orbital arc that will take millions of years to complete. You will not see the next sample, nor will anyone else alive today. The measurement is in the most literal sense a contribution to a record that no individual will ever have the opportunity to finish. The mind quietly registers in the face of this a particular kind of humility. Not the humility of ignorance, of not knowing something that could in principle be known, but the humility of scale, of being embedded in a process so much larger than any single observing life that participation in it is necessarily partial, necessarily incomplete, and yet still meaningful. The measurement matters even though the story it is part of will not resolve in any time frame any human being will inhabit. Evidence suggests that when supermassive black holes do eventually merge, when the binary finally closes and the two objects coalesce into one, the event releases gravitational waves on a scale that no merger of stellar mass black holes approaches. The amplitude of these waves travelling outward through space-time at the speed of light carries information about the masses and spins of the merging objects, about the final moments of inspiral, about the brief and extraordinarily energetic moment of coalescence. This signal, travelling across millions or billions of light years, will eventually pass through the Earth, already may be passing through the Earth, as background gravitational wave noise accumulated from all the supermassive black hole mergers that have occurred throughout cosmic history. Detecting this background, the cumulative gravitational wave signal from all the binary supermassive black hole mergers in the observable universe has become one of the active frontiers of observational astrophysics. Pulsar timing arrays, which monitor networks of millisecond pulsars distributed across the galaxy with extraordinary precision, have begun to detect signals consistent with the existence of this gravitational wave background. The signal is faint, and disentangling it from other sources of timing noise requires years of accumulated data. But the early indications are consistent with what would be expected from a universe populated with merging supermassive black holes at the rate that galaxy merger statistics would predict. What researchers have found is that the universe is in a very real sense humming. Not with sound cannot propagate through the vacuum of space, but with the geometric vibration of space-time itself set into oscillation by the slow, spiral, and eventual union of the most massive bound objects in the cosmos. This background hum is present everywhere, always passing through every object in the universe, including the planet we inhabit. We cannot feel it. Our bodies are not sensitive enough. The distortions it produces in the fabric of space are smaller than the diameter of a proton. But they are real, and they carry encoded in their frequencies and amplitudes a record of the entire history of supermassive black hole mergers stretching back through cosmic time. It seems that even silence examined carefully enough turns out to contain something. The dual black holes in their slow inward spiral are among the many strange things the universe contains, perhaps the ones that most fully embody the particular character of cosmic patience. Not the patience of waiting, of something that would prefer to be finished but must endure the interval, but the patience of a process that unfolds at exactly the rate the physics allows, neither hurried nor delayed, moving toward its outcome across millions of years, with the same unhurried certainty that a river moves toward the sea. And there is a galaxy not far in cosmic terms from our own that carries a different kind of strangeness, not the strangeness of two hearts slowly converging, but the strangeness of a heart that moves against the current of everything around it, drifting in a direction that the large-scale structure of the universe, according to every model, should not permit. Something about the way it moves has been puzzling astronomers for decades, and the explanation, when it began to emerge, turned out to be one of the more quietly unsettling findings in the recent history of cosmology. There is a current in the universe, not a current in the way rivers have currents, not a flow of water moving through a fixed medium, but a large-scale motion, a drift of galaxies and galaxy clusters across enormous distances, pulled in a consistent direction by something whose nature is still being debated, and whose full extent has not yet been mapped. It is one of the quieter discoveries of modern cosmology, and one of the more difficult to absorb because it requires holding in mind simultaneously the expansion of the universe and the existence of something moving against that expansion, or at least orthogonally to it, with a persistence and a scale that the standard models of structure formation struggle to accommodate. To understand it, it helps to begin with what is expected. The universe on its larger scales is expanding. Every galaxy is moving away from every other galaxy, not because galaxies themselves are moving through space in the conventional sense, but because the space between them is growing. This expansion is isotropic, meaning it proceeds at the same rate in all directions, producing a universe in which on average the distribution of matter is uniform, and no direction is privileged over any other. Within that expanding framework, individual galaxies and galaxy clusters have what astronomers call peculiar velocities motions, relative to the smooth expansion caused by the gravitational pull of nearby concentrations of mass. A galaxy in the vicinity of a large cluster will be drawn toward that cluster, acquiring a velocity component that is not simply the expansion, but is superimposed on it. These peculiar velocities are normal, expected, and well accounted for in the standard model. They are the local texture of a universe that is expanding smoothly on large scales, but lumpy on small ones. What is not so easily accounted for is a motion that extends across scales far larger than any individual cluster, a coherent drift of a significant volume of the universe in a consistent direction, as though something very massive located somewhere outside or at the extreme edge of the observable universe is exerting a gravitational pull on an enormous region of space. This motion was first clearly identified in the late 1980s through careful measurements of the peculiar velocities of galaxies across a large region of the sky. When researchers corrected for the motions expected from nearby structures, a residual drift remained a systematic motion of thousands of galaxies spread across hundreds of millions of light-years, all moving in roughly the same direction with a velocity of several hundred kilometers per second. The region of space toward which this drift appeared to be directed was located in the general direction of the constellation Centaurus, beyond the concentration of galaxy clusters known as the Great Attractor. The Great Attractor itself, a large overdensity of matter centered roughly 250 million light-years away, was identified as a partial explanation for the observed motions. It is a genuine concentration of mass containing the equivalent of tens of thousands of galaxies, and it does exert a gravitational influence on the surrounding region. But subsequent more precise measurements revealed that the Great Attractor alone was not sufficient to account for the full observed drift. Something further away more massive was also contributing. That something was eventually traced in part to an even larger structure, a massive concentration of galaxy clusters approximately 700 million light-years distant in the direction of the constellations Vela and Centaurus, which has come to be known as the Shapley supercluster. The Shapley supercluster is one of the most massive concentrations of matter in the observable universe, containing the equivalent of more than 10 million billion solar masses spread across a region roughly 500 million light-years across. Its gravitational influence is felt across vast distances, contributing significantly to the large-scale peculiar velocity field in our region of the cosmos. Evidence suggests that even accounting for the Shapley supercluster, some residual systematic motion remains unexplained. The picture is not yet complete, and different analyses of the available data reach somewhat different conclusions about what fraction of the observed drift has been accounted for and what remains to be explained. Scientists are still exploring the full extent and origin of this large-scale coherent flow, in part because mapping it accurately requires peculiar velocity measurements for galaxies spread across enormous volumes, a technically demanding undertaking that is still in progress. What is striking about this situation is not simply the motion itself. Large-scale flows of matter are not in principle unexpected, but the scale on which it appears to operate. Standard cosmological models predict that coherent flows should become increasingly small on scales larger than a few hundred million light-years as the universe approaches the homogeneity that the cosmological principle requires on large scales. The flows that have been measured appear in some analyses to persist to scales larger than models comfortably accommodate. The degree of tension between observation and prediction is a matter of ongoing discussion. Some researchers consider it a genuine anomaly, requiring explanation. Others consider it within the range of statistical variation expected from a finite imperfect survey. But within this broader flow there are individual galaxies whose motions are more specifically puzzling. Galaxies that appear to be moving in directions inconsistent with the gravitational sources identified in their vicinity, objects whose trajectories, when examined carefully, suggest the influence of something that has not yet been accounted for. One of the more discussed examples in recent years involves observations of galaxies in the region known as the dipole repeller, a large underdensity of matter whose gravitational effect is in a sense the opposite of an attractor. While the Shapley supercluster and the Great Attractor pull surrounding galaxies toward them, the dipole repeller pushes them away not through any active repulsive force, but through the absence of the gravitational pull that would otherwise be present. Galaxies in the vicinity of this void are not being attracted toward it. They are being pulled away from it by the structures on its far side, and the relative weakness of gravitational attraction from the void's direction allows that pull to dominate. Researchers have found that including the dipole repeller in the model of large-scale flows significantly improves the agreement between predicted and observed galaxy motions in the local universe. The local group, the small cluster of galaxies that includes the Milky Way Andromeda, and their smaller companions appears to be moving both toward the Shapley supercluster region and away from the dipole repeller, with the two effects combining to produce the observed motion. The dipole repeller itself sits in the direction roughly opposite to Shapley, creating what amounts to a gravitational gradient, a slope, in the large-scale distribution of matter down which the local group is slowly sliding. The mind tends to find a particular quality of strangeness in the idea of a repeller, a region of space whose primary influence is its absence. We are accustomed in ordinary experience to thinking of forces as things that push or pull, active agencies with a direction and a magnitude. The dipole repeller exerts no force at all, it simply fails to attract. And that failure in a universe where gravity is omnipresent and every mass pulls on every other mass becomes in relative terms a kind of negative influence, a hole in the gravitational landscape through which the local universe has been slowly, continuously falling for billions of years. What we understand so far suggests that the full mapping of a large-scale structure and its associated velocity fields will require the next generation of galaxy surveys programs that will measure the positions and distances of tens of millions of galaxies across volumes far larger than any current dataset covers. These surveys are already in various stages of planning and early execution, and the data they produce over the coming decades will, researchers expect, significantly clarify the picture of what is pulling and what is pushing in the large-scale universe. It seems that in this domain, the domain of flows that persist across hundreds of millions of light-years of attractors and repellers, operating on scales that dwarf any individual galaxy, the universe is revealing something about its large-scale architecture that is still being decoded. The structure of the cosmic web, the network of filaments, walls, clusters and voids that constitutes the large-scale distribution of matter is not simply a static arrangement. It is a dynamic landscape, and the motion of every galaxy within it is shaped by the gravitational influence of all the other structures within the observable horizon. In that landscape, there are galaxies whose motions simply do not fit, galaxies that appear when the expected contributions from known structures are subtracted to be moving in directions that current maps cannot account for. Some of these may reflect errors in distance measurement. Peculiar velocity analyses are exquisitely sensitive to how accurately distances are known, and errors propagate into apparent velocities in ways that are difficult to fully control. Others may reflect structures that exist beyond the current survey boundaries, exerting influence on the observable region without themselves being visible. And some perhaps point towards something genuinely unaccounted for in the current picture, some feature of the mass distribution in and around the observable universe that the standard framework has not yet incorporated. The observable universe, after all, is bounded not by any physical wall, but by the finite speed of light combined with the finite age of the cosmos. There is almost certainly more universe beyond that horizon, and what it contains, whether its mass distribution continues the patterns visible within the observable region, or differs from them in ways that would produce flows and asymmetries detectable from inside, is something that cannot even in principle be observed directly. It may be that some of what pulls at the galaxies in the local universe originates in regions of space that light from those regions has not yet had time to reach us. The gravitational influence of matter propagates in the context of general relativity in ways that are coupled to the expansion of the universe in complex and not entirely intuitive ways. What is pulling on the Milky Way from beyond the observable horizon is genuinely unknown, not unknown in the sense of data not yet collected, but unknown in the sense of inaccessible in principle to any observation. Studies indicate that this particular aspect of cosmology, the question of what lies beyond the observable edge and how it influences what is within, occupies a genuinely strange epistemological position. It is a question that physics can address theoretically through the mathematics of how initial conditions propagate over time, but that observation cannot directly answer. The boundary is not a wall that better telescopes will eventually see past. It is a horizon in the relativistic sense, a surface beyond which information cannot reach us, because the universe has expanded too much, and light has not had time to cross the distance. Sitting with that boundary quietly, not with frustration, not with the urgency of a question that demands an answer, there is something almost restful in it. The acknowledgement that some things are genuinely beyond reach, that the map has an edge, and the edge is real, and what lies beyond it is not simply unknown but unknowable in the strictest sense. Not forever if the universe's expansion were to slow and reverse, if the geometry of space-time were to change in ways currently not predicted but under any conditions we can currently model or measure. The galaxy moving against the current is in this broader context a small detail in a very large picture, a single data point in a map that is still being drawn. But it points in its small and specific way toward the same recognition that the strange galaxies have been pointing toward throughout this long unhurried journey through the cosmos. The recognition that the universe is larger, more structured and more surprising than the models built to describe it, and that each anomaly, each motion that does not fit each galaxy that should not exist as it does, is a thread leading towards something not yet understood. And there are threads of a different kind woven not through space, but through time, through the long history of how matter has arranged itself into structures, and how those structures have left marks on one another that persist for billions of years after the original encounter has ended. The marks left on galaxies by the things that passed through them, or near them, or merged with them long ago, those marks are still there. Quiet encoded in the distribution of stars and gas, and the orbital memories of objects moving through the dark. Every encounter leaves something behind, not always something visible, not always something that can be pointed to and named in a single observation. But in the patient accumulative language of physics, nothing passes through the gravitational field of another object without both parties being changed by the interaction. The change may be small, it may be distributed across a population of stars so broadly that no single orbit looks different from what it would have been otherwise. But it is there encoded in the collective motion of matter preserved in the arrangement of structures that formed in the aftermath of something that happened long ago. Galaxies carry these records in their stellar streams. A stellar stream is in its simplest description a trail of stars drawn out from a smaller galaxy or globular cluster by the tidal force of a larger one stretched along the smaller object's orbit into a long, thin arc that traces the path it has travelled. It forms the same way that water trails behind a moving boat, not because the water is being pushed in that direction, but because it is being left behind, displaced from the parent structure by the differential gravitational pull of the larger system it is moving through. Researchers have found dozens of stellar streams in the halo of the Milky Way alone. Some are the remnants of dwarf galaxies that strayed too close and were gradually dismembered over billions of years, their stars stripped layer by layer with each successive orbit until essentially nothing of the original structure remained except the stream itself. A ghost of a galaxy, its presence detectable only in the subtle alignment and common motion of stars spread across a wide arc of the sky. Others come from globular clusters, the dense ancient balls of stars that orbit in the outer reaches of large galaxies, and which when disrupted leave thinner, more precisely defined trails that can persist for billions of years. The Sagittarius stream is perhaps the most thoroughly studied example. The Sagittarius dwarf galaxy, currently in the process of being absorbed by the Milky Way, has been orbiting our galaxy for billions of years, and with each orbit the tidal forces of the Milky Way have stripped stars from its outer regions, leaving them behind in a stream that now wraps around the Milky Way in multiple loops, a structure so large that it subtends a significant fraction of the entire sky, visible in careful surveys as an overdensity of stars following a great circle around the galaxy. What we understand so far suggests that the Sagittarius stream has completed several wraps around the Milky Way, with the most recent debris still relatively close to the progenitor galaxy, and the oldest material stretched into loops that have spread and diffused over billions of years of orbital evolution. The stream carries stars of different ages and compositions, each reflecting the conditions at the time they were stripped a stratigraphic record in stellar terms of a long history of interaction, preserved in the positions and velocities of individual stars spread across hundreds of thousands of light years. The study of stellar streams is at its core an exercise in reading the past from the present configuration of matter. Because tidal stripping is a predictable process governed by well-understood gravitational physics, the current positions and velocities of stream stars contain information about the orbit of the progenitor, the mass distribution of the host galaxy, and the history of any perturbations the stream has experienced since it formed. By carefully modelling streams and comparing the models to observation, astronomers can in effect use the streams as probes of the gravitational potential, the invisible scaffolding of mass including dark matter that determines how things move within a galaxy. This is a method with remarkable sensitivity. A stream of stars spread over tens of thousands of light years and observed with sufficient precision responds to density variations in the dark matter halo through which it passes in ways that produce subtle gaps, kinks, and density variations in the stream itself. If the dark matter in a galaxy's halo is smoothly distributed, the stream should be similarly smooth and continuous. If the dark matter is clumped, if it exists in discrete substructure, in smaller concentrations embedded within the larger halo, those clumps will gravitationally scatter individual stars out of the stream as they pass by, creating gaps that persist and widen over time. Evidence suggests that detecting these gaps is one of the most promising methods for testing whether dark matter behaves as current particle physics models predict. The standard model of cold dark matter, the dominant theoretical framework, predicts that dark matter halos should contain large numbers of smaller subhalos, remnants of the hierarchical process by which large structures grew from the merging of smaller ones. Many of these subhalos are too small to have accumulated enough ordinary matter to form visible galaxies, and would therefore be entirely invisible by conventional means. But if they are there, they should leave their mark on stellar streams, a population of gaps and distortions, whose statistical properties can be compared with the predictions of the model. Several stellar streams in the Milky Way halo have been identified as candidates for showing this kind of gap structure. The analysis is technically demanding because other processes, the bar at the centre of the Milky Way, the spiral arms known satellite galaxies, can also perturb streams in ways that produce apparent structure. Distinguishing the signature of dark matter substructure from these other effects requires careful modelling and ideally very precise measurements of the positions and velocities of individual stream stars, measurements that have become increasingly feasible with the data from the Gaia Space Telescope, which has mapped the positions and motions of nearly 2 billion stars in the Milky Way with extraordinary precision. It seems that the Milky Way is in this sense its own laboratory, a galaxy close enough to examine in exquisite detail, containing within its structure the preserved records of billions of years of gravitational interaction available for study in a way that no external galaxy can be. The stellar streams in its halo are in the most literal sense fossils, not fossils of organisms but fossils of motion, preserved trajectories encoded in the positions of stars that continue to move along paths set in place by encounters that ended long before the Earth formed. The mind tends to find something quietly moving in this particular kind of permanence. The idea that the universe keeps records not in any purposeful or deliberate way, but simply because physics is conservative, because information once encoded in the positions and velocities of matter does not vanish easily. It diffuses, it spreads, It becomes harder to read with each passing orbit as the stream stars slowly mix with the background population of halo stars. But the information does not entirely disappear. It merely becomes over time more difficult to extract. Beyond the Milky Way, streams and other tidal debris structures have been detected in a growing number of nearby galaxies. The Andromeda Galaxy, our nearest large neighbour, displays an extraordinary wealth of tidal structure in its outer regions, a complex network of shell streams and overdensities of stars that testifies to a history of minor mergers and accretion events as rich, and possibly richer, than the Milky Way's own. Studies indicate that Andromeda has absorbed numerous dwarf galaxies over its lifetime, and the evidence of those absorptions is written in the disturbed multi-layered structure of its extended stellar halo. The shells visible in Andromeda's halo are a particularly evocative form of tidal debris. When a small galaxy falls into a larger one along a nearly radial orbit, approaching almost directly, rather than on a wide circular path, its stars after the progenitor is disrupted tend to accumulate near the turning points of their orbits, the places where they slow reverse and begin to fall back inward. These accumulation points form thin, coherent shells, arc-like overdensities of stars that wrap around the host galaxy in nested layers, each shell corresponding to a different phase of the disruption process. Shells are fragile structures. They disperse over time as orbital frequencies spread across the stellar population. Finding multiple well-defined shells in a galaxy's halo implies a relatively recent disruption event, one that occurred within the last few billion years geologically speaking. Researchers have found that the presence of shells, streams, and other tidal features in a galaxy's halo can be used to reconstruct not just the fact of past mergers, but something of their geometry and timing. The shape of a shell encodes information about the orbit of the progenitor. The stellar populations within the stream, the ages and chemical compositions of the stars reflect the properties of the galaxy that contributed them, and the overall richness of the tidal structure in a galaxy's halo is a rough measure of how many accretion events have occurred, how many smaller galaxies have been consumed over the course of its history. In this sense, the outer halos of large galaxies are archives, repositories of accumulated history where the evidence of past encounters is preserved in a form that with sufficiently precise observations and sufficiently careful modelling can be read back out. The archive is imperfect, time blurs the records, orbital mixing erases the finer details, but it is real, and it contains information that no other method can access as directly. What researchers have found as surveys of nearby galaxy halos have expanded and deepened is that essentially no large galaxy has a perfectly smooth, undisturbed halo. All of them show some evidence of past interactions, some subtle, some dramatic, some so recent that the disrupting satellite is still partially intact at the centre of the debris structure. The smooth, featureless halo of textbook illustrations is, it seems, an idealization. The real universe is messier, more historical, more palimpsest than portrait layers of old events written over one another, each partially obscuring the one beneath but none entirely erased. The Milky Way's own history as reconstructed from its stellar streams and halo populations turns out to be surprisingly eventful. Beyond the ongoing absorption of the Sagittarius dwarf galaxy, evidence suggests several major merger events in the Milky Way's past, including a collision with a substantial galaxy sometime between 8 and 11 billion years ago, an event that has been named the Gaia Enceladus or Gaia Sausage merger, after the distinctive elongated distribution of the stellar orbits it left behind. This ancient merger may have contributed a significant fraction of the stars now found in the inner halo of the Milky Way, and may have played a role in forming or thickening the thick disk, a structural component of the galaxy, distinct from the thin disk in which the Sun resides, and thought to have formed or been significantly heated by this early collision. It may be that the Sun itself owes something of its current position, current orbit, and perhaps even the chemical composition of the cloud from which it formed to events that occurred billions of years before it existed, events whose influence propagated through the galaxy's structure and subtly shaped the conditions under which the solar system eventually assembled. The connection is indirect, distributed across enormous timescales, and impossible to trace with any precision. But it is not in principle absent. Everything in a gravitational system is connected to everything else across time as well as space. There is something in that connectivity that the mind settles into rather than presses against. Not the connectivity of intention or design, not the idea that things were arranged for a purpose, but the connectivity of physics, of a universe where every interaction leaves a residue, where the past is never entirely absent from the present, where the arrangement of matter right now contains distributed across its structure the accumulated record of everything that has ever happened to it. The stellar stream arcing across the Milky Way halo, the shells in Andromeda's outer regions, the disturbed morphology of a galaxy that passed too close to a neighbour 1 billion years ago. These are all in different registers and at different scales the same thing. The universe's memory of itself, written not in any language, not in any code designed to be read, but in the simple, indelible script of physical consequence. Things happened here, and the arrangement of matter reflects that they happened, and will continue to reflect it for longer than any timescale we can comfortably name. The records galaxies keep are not only written in their stars. There is a layer deeper than the stellar distribution, quieter, less visible, but in some ways more fundamental, where the history of a galaxy is preserved in forms that no optical telescope can easily reach, and that require a different kind of patience to read. The patience of listening for frequencies of light that the human eye was never designed to detect. Frequencies that carry in their emission and absorption the story of matter in its most elemental form. The mind, it seems, has been keeping something still and patient all along, and what the quietest frequencies of the universe have been whispering across all this time is something that changes how we understand not just galaxies, but the very atoms from which everything, including the listener resting now in the dark, is made. There is a frequency of light that hydrogen emits when it transitions between two very specific energy states, a frequency so precisely defined, so stable across all of space and all of time, that astronomers have used it as a kind of universal reference tone, a tuning fork for the cosmos. It falls in the radio portion of the spectrum at a wavelength of approximately 21 centimeters, and it is produced wherever neutral hydrogen exists, which is to say it is produced almost everywhere. Hydrogen is the most abundant element in the universe. It constitutes roughly 3/4 of all ordinary matter by mass. It was the first element to form in the minutes following the beginning of everything, when the universe had cooled enough for protons and electrons to combine into stable atoms. It is the fuel from which stars are born, the medium through which galaxies accumulate their raw material, the tracer of large-scale structure that connects the dense regions of clusters and filaments to the vast, nearly empty voids between them. And it speaks in radio wavelengths continuously and without pause, in a signal that has been travelling through the universe since long before the Earth existed. The 21 centimetre line, as it is known, has been one of the most powerful tools in radio astronomy since its first detection in the early 1950s. By mapping the distribution of this emission across the sky, astronomers can trace the distribution of neutral hydrogen in and around galaxies, not just where the stars are, but where the gas is. The gas that has not yet formed into stars that lies in the outer disks of galaxies, and in the filaments connecting them that is being accreted or expelled, that constitutes the reservoir from which future star formation will draw, Researchers have found that the neutral hydrogen distribution in a galaxy often extends considerably further than the visible stellar disk. In many spiral galaxies, the gas disk is 2 to 3 times the diameter of the region, where stars are concentrated a vast diffuse halo of raw material surrounding the luminous body of the galaxy, slowly flowing inward to feed the ongoing process of stellar birth at the center. This extended gas reservoir is in a sense the galaxy's future, the material from which the next generations of stars will eventually be built on timescales that dwarf any human frame of reference. Mapping this gas has revealed details about galaxy structure and dynamics that are invisible in ordinary starlight. The rotation curves of galaxies, the measurements that first provided compelling evidence for dark matter, through the observation that stars in outer regions orbit faster than the visible mass alone would allow, were in many cases extended and refined, using 21 centimeter observations of gas at radii, far beyond the reach of optical stellar spectroscopy. The gas traces the gravitational potential to larger radii than stars do, providing a more complete picture of the mass distribution, and making the dark matter signature more apparent. It may be that no single observational tool has contributed more to our understanding of galactic structure than the ability to listen to hydrogen. Not to see it in the ordinary sense, but to detect the radio waves it emits, to tune in effect to the frequency at which the universe's most abundant element broadcasts its presence, and to map that presence across the sky with a precision that optical telescopes, for all their power, cannot replicate for this particular tracer. Beyond its use as a structural tracer within galaxies, the 21 centimeter line has become central to one of the most ambitious observational programs in contemporary cosmology. The effort to map the large-scale distribution of neutral hydrogen across cosmic time using the fact that the expansion of the universe redshifts the emission to progressively longer wavelengths as you look further back into the past. By observing at different radio frequencies, radio telescopes can in principle isolate the 21 centimeter emission from hydrogen at different cosmic epochs, building a three-dimensional map of where the gas was at different points in the history of the universe and how its distribution evolved as structures formed and galaxies developed. This program, known as 21 centimeter intensity mapping, is still in its early stages. The signal is extraordinarily faint at cosmological distances, and separating it from the much brighter emission of foreground radio sources requires sophisticated data processing and instrument design. But the potential is significant, the ability to map the large-scale distribution of matter, not just at the present epoch, but across a substantial fraction of cosmic time, using a tracer that probes both ordinary matter and indirectly the dark matter scaffolding within which ordinary matter is embedded. Scientists suggest that the full realization of this program with next-generation radio telescope arrays, covering large fractions of the sky with high sensitivity, could provide constraints on the expansion history of the universe and the properties of dark energy, the mysterious component responsible for the acceleration of cosmic expansion, comparable to, or better than those available from any existing method. The universe, it turns out, has been broadcasting its large-scale structure in radio waves all along. We're only now developing the instruments capable of receiving the full message. The question of dark energy is one that sits at the edge of what current understanding can reach, and it is worth approaching gently without the urgency that the word energy might suggest. It was identified through observations of distant supernovae in the late 1990s, a Nobel Prize-winning discovery that revealed the expansion of the universe is not slowing down, as gravity alone would predict, but accelerating. Something is causing the expansion rate to increase over time, working against the gravitational tendency of matter to draw together. That something has been given the name dark energy, and it constitutes approximately 68% of the total energy content of the universe, making it by a considerable margin the dominant component of everything that exists. What dark energy is, whether it is a property of empty space itself, a new and unknown field permeating the cosmos, or something else entirely, is not known. Evidence suggests that its behavior is consistent within current observational precision, with the simplest possible model, a constant energy density associated with the vacuum, unchanging over time and uniform in space. This is the cosmological constant, a term that appears naturally in the equations of general relativity, and that was interpreted by its discoverer as a kind of repulsive term built into the geometry of space-time itself. But the consistency with a cosmological constant does not rule out alternatives. A dark energy that changes slowly over time, or that varies slightly from place to place, would produce observational signatures that are only marginally different from a pure cosmological constant at current levels of precision. Distinguishing between these possibilities requires measurements of the expansion history and large-scale structure with significantly better accuracy than is currently available, which is one of the primary scientific motivations for the next generation of galaxy surveys and radio telescope programs. What we understand so far suggests that dark energy began to dominate the universe's energy budget approximately 5 billion years ago, roughly at the time when the solar system was forming. Before that point, matter density was high enough that gravity modestly slowed the expansion. Since then, the accelerating expansion driven by dark energy has been gradually pushing the large-scale structure of the universe apart, increasing the distances between galaxy clusters, reducing the rate at which new structures form, and setting the cosmos on a long trajectory toward increasing diffuseness and isolation. The far future of the universe extrapolated from this trajectory is a picture that invites a particular quality of reflection. If the acceleration continues, and there is currently no observational evidence that it will not, the galaxies beyond the local group will over tens of billions of years be redshifted to wavelengths that no instrument can detect their recession velocities, exceeding the speed of light in the way that becomes possible when it is space itself, expanding rather than objects moving through it. The local group will eventually merge into a single large elliptical galaxy, slowly burning through its remaining stellar fuel, while the rest of the observable universe recedes beyond any possibility of observation or interaction. The brain tends to interpret this prospect through the emotional register available to it, which includes something that functions like a sense of vastness of scale, exceeding comprehension of time, stretching beyond anything that personal experience or imagination can fully populate. But sitting with it gently without pressing for a response, there is something in the image that is not desolate. A universe that expands into quiet, that moves slowly and continuously toward a kind of solitude that is also a kind of completeness. Every process running its full course, every star eventually going dark, every orbit slowly widening, every connection between distant structures eventually severed by the patient work of expanding space. It seems that the universe at its larger scales is moving toward rest. Not the rest of stasis, not the rest of nothingness, but the rest of a process that has been running for a very long time and will run until every available energy gradient has been exhausted. Cosmologists have names for the stages of this long unwinding, the stelliferous era in which stars burn, the degenerate era in which white dwarfs and neutron stars slowly cool, the black hole era in which only the most massive objects persist, and the dark era in which even those have decayed, leaving a universe of maximum entropy, maximum diffuseness, and no further gradients to drive any process at all. These timescales are so immense, measured in years with exponents that require their own notation, that they bear no meaningful relationship to anything in human experience. They are not frightening in the way that immediate endings are frightening. They're simply large in a way that the mind can acknowledge without fully inhabiting. Researchers have found something curious in the study of galactic evolution across cosmic time, a pattern that mirrors in its broad outline the long arc of stellar birth and death. The rate of star formation across the universe as a whole peaked approximately 10 billion years ago in the era known as cosmic noon, when the universe was roughly 3 to 4 billion years old. At that time, galaxies were forming stars at a rate perhaps 10 times higher than the average rate today. Since then, the overall rate of star formation has been declining slowly but consistently, as the available reservoir of cold gas in galaxies is gradually consumed, expelled or prevented from cooling by the feedback processes associated with supermassive black holes and stellar evolution. The universe is in this sense past its most generative phase. The great era of star formation, the epoch in which the majority of the stars that will ever exist in the observable universe were being built, is already behind us. What remains is the long, slow burn of what was made during that era, and the occasional new burst of formation triggered by mergers or the accretion of fresh gas. But the overall trajectory is one of gradual quieting of a universe that built most of what it will ever build, and is now settling into the long patient process of living on what it made. There is a particular resonance in that image for a listener resting in the quiet of the night. The universe building most of what it will build, and then slowly over immense timescales growing quieter. The stars that burn most brightly living the shortest lives, the ones that burn most softly persisting the longest. The whole vast enterprise of cosmic structure building proceeding not toward an endpoint of greater complexity and density, but towards something more like a gradual, immensely unhurried dissolution. The atoms in a human body were forged in stars that have long since ended. The calcium in bone, the iron in blood, the oxygen drawn in with each breath, each of these elements was produced in the nuclear furnaces of stellar interiors, released in the deaths of those stars dispersed through space, and eventually incorporated into the gas cloud from which the solar system formed. We are each of us a temporary arrangement of matter that has been through multiple cycles of stellar birth and death, and will return to the interstellar medium in some form eventually. The universe has loaned these atoms to this particular arrangement for a brief interval, and will in due course take them back. This is not a melancholy thought sitting with it quietly. It is simply the view from a sufficient distance, the recognition that the matter that constitutes living things is not separate from the matter that constitutes galaxies but continuous with it. That the strange galaxies described throughout this long, slow journey are not elsewhere, not distant from the listener in any way that is truly separating. The atoms in the body listening now pass through the interiors of stars. They were scattered in supernova explosions. They drifted through the interstellar medium for hundreds of millions of years. They condensed into a planet, into oceans, into life, into this particular configuration of matter that is right now lying in the dark and listening to the universe describe itself. The connection between the listener and the strangest galaxy ever discovered is not metaphorical. It is physical. It is atomic. It is written in the same conservation laws that govern the motion of stellar streams and the slow spiral of binary black holes. The universe that contains these objects also contains the person resting now, and both are made of the same material, following the same rules, moving through the same expanding space. And in the long arc of what the universe has been doing, building, merging, disrupting, recording, slowly, quieting what it has been doing among other things, is arranging itself into configurations complex enough to wonder about their own origin, to lie in the dark and ask what the light means, to be moved quietly and without quite knowing why by the image of a galaxy stretched into transparency, or a ring of stars still expanding from a collision that happened before the Earth existed. That capacity for being moved, for receiving the strangeness of the cosmos and finding it in some register below language, beautiful seems to be one of the things the universe has been building toward in its patient and unhurried way since the first moments of everything. And somewhere in the long history of how that capacity came to exist in the specific extraordinary chain of events that led from the formation of the first hydrogen atoms to the emergence of creatures capable of wondering about them, there is a story that the cosmos has been quietly composing all along in the frequency of its own light. One that was always there waiting only for something complex enough to listen. Part 11. The universe that learned to notice itself. Word count 3150. There is a question that sits quietly at the edge of cosmology, not a question that appears in the technical literature in quite this form, but one that the technical literature taken together and held at a slight distance seems to be circling around without quite naming. The question is this: what does it mean that the universe contains things capable of studying the universe, not as a philosophical provocation, not as a setup for a conclusion about purpose or design, simply as an observation, a fact that when examined with the same patient attention that astronomers bring to stellar streams and supermassive black holes, turns out to be genuinely strange. Strange in the way that the best scientific strangeness is not invented, not embellished, but simply noticed. The universe began as a smooth, hot, structureless plasma. 13.8 billion years later, it contains arrangements of matter that can receive light from galaxies billions of light years away, process the information it carries and construct from that information an account of where they come from. That is not nothing. That is by any measure a remarkable thing for a universe to have done. Researchers have found in the study of how complexity arises in physical systems that the emergence of structure from simplicity is not accidental, but follows from the fundamental laws in ways that are, in retrospect, almost inevitable. Given the initial conditions of the early universe, the slight density variations seeded into the primordial plasma, the specific values of the fundamental constants, the particular properties of gravity and electromagnetism, and the nuclear forces, the long-term evolution of the cosmos toward increasing complexity, was if not guaranteed at least deeply probable. The pathway from hydrogen to beings capable of wondering about hydrogen runs through several distinct stages, each of which required the previous one and enabled the next. Hydrogen and helium formed in the first few minutes provided the raw material for the first generation of stars, massive short-lived objects that burned hot and fast, producing in their interiors the heavier elements that hydrogen and helium alone cannot become: carbon, oxygen, nitrogen, silicon, iron. Each of these was forged in stellar nucleosynthesis, in processes that require the temperatures and pressures found only in stellar cores and released into the interstellar medium when those stars ended their lives. It seems that this process stars forming, burning, dying, and seeding. The surrounding gas with the elements they produced is not merely a background feature of cosmic evolution. It is in a real sense the mechanism by which the universe built the complexity that would eventually become everything else. Each generation of stars enriched the interstellar medium with heavier elements, making the next generation of stars and the planetary systems around them progressively richer in the chemistry of complexity. The solar system formed from gas that had already been through several cycles of this enrichment gas that contained in the proportions needed to build rocky planets and organic molecules, the products of many stellar lives. The Earth specifically is a repository of this enrichment. Its composition, the silicate mantle, the iron core, the thin layer of water covering much of its surface, The carbon-based chemistry of its biosphere reflects the particular history of the part of the galaxy in which it formed and the specific properties of the stellar generations that preceded the solar system in that region. The Earth is in this precise sense a piece of galactic history, a condensed record of several billion years of stellar nucleosynthesis, gravitational dynamics and chemical evolution, arranged by the specific sequence of events that led to the formation of this planet at this location at this time. Evidence suggests that planetary systems similar to the solar system are common throughout the galaxy. The last 3 decades of exoplanet research, the study of planets orbiting stars other than the Sun, have revealed that planets are not the exception, but the rule. Essentially, every Sun-like star in the galaxy appears to host a planetary system of some kind, and the statistics suggest that rocky planets in the habitable zones of their stars' regions, where liquid water could exist on the surface, are numerous. The precise abundance depends on assumptions that are still being refined, but the current estimates suggest billions of potentially habitable rocky planets in the Milky Way alone. What this implies for the question of life and for the broader question of whether the universe has elsewhere and otherwise developed the capacity to notice itself is genuinely open. Scientists are still exploring the conditions under which life originates, and the question of whether the origin of life is a common or rare event given the right chemical conditions remains one of the deepest unsolved problems in science. The single example available for direct study life on Earth provides extraordinarily detailed information about one particular pathway from chemistry to biology, but cannot by itself distinguish between a universe in which that pathway is commonly travelled and one in which it is vanishingly rare. What researchers have found is that the chemical precursors of life, amino acids, nucleotides, sugars, and the other molecular building blocks that biology depends on, are not unique to Earth. They are found in meteorites, in comets, in the interstellar medium. The chemistry of life, or something very like it, appears to be distributed widely through the galaxy, produced by the same processes of organic chemistry that operate wherever carbon, hydrogen, oxygen, and nitrogen are present in the right proportions under the right conditions. Whether that distributed chemistry has elsewhere crossed the threshold from complex molecules to self-replicating systems to the kind of organized biology that eventually produces curiosity about galaxies that is not known. The mind quietly registers a particular kind of patience that this question requires. Not the patience of waiting for an answer that is on its way, but the patience of holding a genuinely open question, one that may not be answerable with current methods, and that may require decades or centuries of further observation and experiment before the evidence is sufficient to draw any conclusion. The search for biosignatures in the atmospheres of exoplanets, the attempt to detect in the spectra of distant planetary atmospheres the chemical signatures of biological processes is underway, with current and near-future telescopes beginning to accumulate data on the atmospheric compositions of rocky worlds. But the precision required to detect subtle biological signatures is at the edge of current capability, and the interpretation of any such detection would require careful elimination of non-biological explanations. There is something in the act of looking, in the careful, precise, technically demanding work of examining the atmosphere of a planet orbiting a star dozens of light years away, and asking whether something there is breathing that carries a quality difficult to name in ordinary language. It is the universe in a sense turning its attention on itself. The matter that formed from the early universe that was processed through generations of stars that assembled into planets, and eventually into biology, and eventually into scientists now directing its observational tools outward again, across the same distances from which the atoms that compose it originally came, asking whether the process that led to it has been repeated elsewhere. Psychologists often note that the human capacity for self-reflection, the ability to think about thinking, to hold the self as an object of attention, is one of the more distinctive features of the kind of consciousness that humans exhibit. It seems that something structurally similar operates at the cosmic level. A universe that began without any structure capable of receiving information about it has over billions of years, and through the patient operation of physical laws produced structure that can not only receive that information, but build from it an account of the universe's own history. The universe, in a meaningful and non-metaphorical sense, did not know itself at the beginning. The knowledge it now contains, distributed across the minds and instruments and accumulated records of generations of scientists, is something it has been building toward for the entirety of its existence. This is not a mystical claim. It is a straightforward description of a physical fact. The laws of physics applied to the initial conditions of the early universe have produced, among other things, the capacity for understanding. That capacity is currently exercised by one species on one planet in one galaxy, among hundreds of billions. Whether it exists elsewhere is unknown, but here for certain, the universe has arrived at the point of looking back at where it came from. What we understand so far suggests that this looking back has a particular character, not the passive reception of information, but an active process of model building and revision, of comparing predictions with observations and adjusting the picture when they do not agree. The strangeness of the galaxies described throughout this long passage through the cosmos is in part a strangeness of expectation, failing of the universe behaving differently than the models built to describe it predicted. And the response to that failure is not to abandon the enterprise, but to revise the models, to collect more data, to develop new instruments and new mathematical frameworks, and to try again. This iterative quality, the willingness to be wrong to correct, to begin again, is, researchers have found, the mechanism by which the understanding accumulated over centuries has actually accumulated. Not through the steady accumulation of correct knowledge, but through the productive failure of incorrect models, each failure pointing toward what the replacement must accommodate. The strange galaxies are not problems in the pejorative sense. They are gifts in the scientific sense, objects whose strangeness marks the boundary of current understanding and points toward the territory beyond it. It may be that the deepest connection between the listener resting in the dark and the strange galaxies described throughout this night is not the atomic connection, not the shared matter, the recycled elements, the supernova debris, but something more subtle. The capacity to be surprised, to encounter something that does not fit the expected pattern, and find in that misfit not frustration, but the particular quality of interest that arises when reality exceeds the models built to contain it. That capacity for genuine surprise in the face of the genuinely strange is in its own way one of the more remarkable things the universe has produced. It requires a certain kind of cognitive flexibility, a certain tolerance for uncertainty, a willingness to let the known give way to the unknown without collapsing the distinction between them. It is not a universal property of complex systems. It is a specific property of the particular kind of complexity that has arisen here on this planet in these minds. Studies indicate that the experience of awe, the response to vastness, to scales and structures that exceed ordinary comprehension, has measurable effects on cognition and well-being. It tends to quiet the default mode of self-referential thinking, the internal narrative that runs continuously in ordinary waking consciousness, and to replace it with something more open, more receptive, more present to what is actually there. Astronomers who spend years studying the large-scale structure of the universe sometimes describe a quality of perspective that their work provides a sense that the ordinary concerns of daily life, while real and important, exist within a context so vast that they naturally assume their proportionate scale. There is in this something worth noticing about what the night sky offers, and what listening to the science of strange galaxies in the slow, soft hours of the night might quietly do. Not instruction, not the accumulation of facts, but something more like the recalibration that happens when attention is held gently and without urgency on something genuinely larger than the self. These strange galaxies are not trying to teach anything. They simply are present, ancient, patient, persisting in configurations that the laws of physics produced, and that the laws of physics sustain indifferent to observation, indifferent to understanding, available to whatever attention finds its way to them across the distance. That a human mind resting in the dark on a small planet in an ordinary galaxy, at the edge of one of the universe's minor filaments, can receive information about them, can hold in awareness the image of a ghost galaxy made almost entirely of invisible matter, or a ring of stars still expanding from a collision 300 million years past, or a binary black hole spiraling inward across a gap that will take 1,000,000 years to close, is when considered directly a fact of considerable strangeness in its own right. The universe arranged itself so that this is possible, whatever that means, and it may mean nothing more than that the laws are as they are, and these are the consequences the fact stands. The attention you bring to these objects is part of what the universe contains, part of its total inventory. Along with the dark matter, the stellar streams the gravitational wave background, the slow expansion toward increasing quiet. There is also this, the capacity for a temporary arrangement of matter to lie in the dark and find itself moved by the light of things that existed long before it did, and will continue to exist long after. That continuity is one of the universe's more quietly sustaining features. The light that left a distant galaxy 500 million years ago is still travelling, still carrying information, still available to whatever instrument turns its attention in the right direction at the right moment. The strangeness that has been moving through this long night of galaxies, the ghost galaxy, the ring, the ancient and too early aged, the diffuse and the disrupted, the binary hearts and the moving against the current, all of it is still there, still present in the sky above. And as the hours deepen and the body settles further into rest, there is one thing left to consider. Not a new discovery, not a final strangeness, but something that the entire journey through these galaxies has been moving slowly toward. Something about what the universe in all its strangeness and all its patience eventually becomes when it has had enough time to let everything quiet down. Something that the oldest light in the sky has been carrying toward us all along. There is a star somewhere in the Virgo cluster that has been drifting through intergalactic space for billions of years without belonging to any galaxy at all. It is not alone in this. Researchers have found that the spaces between galaxies in dense clusters are populated with stars that were stripped from their host galaxies, long ago torn free by tidal forces during close encounters flung outward into the intergalactic medium, and left to travel through the darkness on their own. These are called intracluster stars, and though each one burns as steadily and as completely as any star embedded in the heart of a spiral galaxy, none of them illuminate anything nearby. None of them warm any planet. They simply burn quietly continuously in the vast and empty space between one galaxy and the next, and the light they produce travels outward in all directions through distances so large that it arrives, if it arrives at all, as the faintest possible contribution to the soft glow that suffuses the space between galaxies. That glow has a name. It is called intracluster light, and it is one of the more quietly moving discoveries of recent observational astronomy, the recognition that the space between galaxies in a cluster is not entirely dark but is softly diffusely illuminated by the accumulated light of billions of stars that no longer belong anywhere. Stars that have been travelling alone for so long that the galaxies from which they were taken have themselves changed beyond recognition. Stars whose light reaching an instrument sensitive enough to detect it carries no address, no origin, no particular direction from which it came, only the steady patient emission of a stellar interior, burning through its fuel in the ordinary way, unremarkable in every respect except the extraordinary solitude of its location. Studies indicate that intracluster light may constitute anywhere from 10 to 40% of the total stellar light in some clusters, a significant fraction of all the starlight in those environments, coming not from galaxies at all, but from this diffuse unaffiliated population of isolated stars. The fraction varies from cluster to cluster depending on the dynamical history of the system, how many mergers it has experienced, how efficiently it has stripped stars from its member galaxies over time. In the most dynamically active clusters, the ones with the richest histories of interaction and disruption, the intracluster light can be genuinely substantial. What we understand so far suggests that mapping the distribution of intracluster light within a cluster reveals something about the cluster's gravitational potential, the three-dimensional shape of the dark matter halo that holds everything together. Because the intracluster stars were stripped from their host galaxies through tidal interactions, their spatial distribution traces the regions where tidal forces have been strongest over the cluster's history, which in turn reflects the underlying mass distribution. The light that falls between the galaxies is not random. It is in its own soft way a record of forces that no instrument can measure directly, a luminous tracer of gravitational history written across intergalactic space. It seems that even emptiness examined carefully enough contains information. The dark between galaxies is not truly dark. It holds distributed across its volume the diluted light of a population of stars so isolated that they represent in some sense the opposite end of the cosmic social spectrum from the dense stellar nurseries at the hearts of starburst galaxies. Those are places of compression and proximity of gas clouds colliding and fragmenting into hundreds of new stars in a relatively small volume. This is the opposite, the maximum possible dispersal, the condition of having been separated from every nearby structure and left to continue in solitude for longer than the Earth has existed. And yet the light continues. It does not stop because there is no one nearby to receive it. It does not dim because the star is lonely, if stars can be said to experience anything at all. It simply radiates as it always has, in the way that the physics of its interior requires fusing hydrogen, maintaining pressure against gravity, maintaining the delicate balance between the force trying to collapse it and the energy trying to expand it for as long as the fuel lasts. The solitude changes nothing about the physics. The light is indifferent to the darkness through which it travels. There is something in that indifference that the mind quietly rests against in the late hours. The universe does not perform its processes for an audience. It does not require witness. The intracluster star burns whether or not any instrument has been pointed at it, whether or not any survey has included its coordinates, whether or not any human mind has ever held the thought of it. Its existence is entirely independent of any awareness of it. Researchers have found, in examining the stellar populations of intracluster light, that the stars tend to be old, predominantly red giants, and stars approaching the end of their hydrogen-burning lives, relics of an earlier era of star formation in the cluster's member galaxies. This makes sense. The older a cluster, the longer its history of tidal stripping, and the more of its originally formed stellar population has been redistributed into the intracluster medium. The stars that are there now are the survivors of that redistribution, old enough to have been among the first populations formed in the cluster's galaxies, and resilient enough, or simply fortunate enough, in their orbital placement to have been stripped rather than destroyed. They are in their quiet way among the oldest objects in the observable universe, still doing exactly what they were made to do. The light from these stars travelling through the intracluster medium eventually leaves the cluster entirely, continuing outward into the intergalactic space beyond, adding its infinitesimal contribution to the diffuse background radiation that permeates the cosmos. This background, the accumulated light of all the stars that have ever burned integrated across the entire history of the universe, is called the extragalactic background light, and it represents in some sense the total luminous output of everything that has ever shone. It is present everywhere, in every direction, at every moment. It passes through this room. It passes through the walls. It passes through the body of the person resting now in the quiet dark. Most of it is invisible to the human eye, redshifted by the expansion of the universe into infrared wavelengths, or concentrated in ultraviolet ranges that the eye was never designed to receive. But it is there. The light of 100 billion galaxies, each containing hundreds of billions of stars accumulated across 13 billion years of cosmic time, distributed uniformly through all of space and passing right now through everything, including the mind that is perhaps beginning to drift. The breath slows, the thoughts thin, the galaxies continue, out beyond the reach of any instrument we have built in directions that have no names, at distances that dissolve all ordinary measures of scale. The strange galaxies that should not exist are going about their quiet business. Dragonfly 44 holds its sparse population of stars against the darkness, held together by something invisible and patient. The cartwheel sends its ring of new stars still further outward, still expanding at 100 kilometers per second, still tracing the shape of something that passed through it long ago. The red and dead galaxies of the early universe sit in their ancient quiet. Their star formation finished their histories complete, in a way that most galaxies will not be for billions of years yet. The binary black holes spiral imperceptibly. The stellar streams arc slowly through the halos of galaxies that absorbed their progenitors before the Earth was formed. The hydrogen broadcasts its signal as it always has at 21 centimeters in every direction from every location in the universe simultaneously, a continuous patient broadcast to which no one needs to listen for it to continue. The cosmic web holds its shape. The intracluster stars burn in their solitude. The universe expands. And somewhere in the direction of the Virgo cluster, the light of a single isolated star is travelling outward through intergalactic space, not toward anything in particular, not away from anything in particular, simply outward as light does at the only speed available to it. It has been travelling for a very long time. It will travel for longer still. It passes through nothing. It diminishes with distance, as all light does, spreading across the surface of an ever larger sphere, growing thinner and quieter with each additional light year. And somewhere along that journey, at some particular point in the darkness between one thing and the next, it becomes too faint to measure. Not gone, just quiet. Just below the threshold where any instrument we have ever built could say, here. This is where it is, still moving, still real, simply beyond the reach of what is listening. The night holds that too, the things just beyond the reach of listening. The faint signals still travelling, the records preserved in stellar orbits, the hydrogen broadcasting in the dark, everything continuing, quietly, at its own pace, in the patient, unhurried way of a universe that has always had more time than anything inside it can imagine. The breath, the dark, the light somewhere still moving, and whatever is resting now between one thought and the next, between one breath and the one that follows, resting in the same expanding space as all of it, part of the same continuous thing, still, drifting, already almost gone,